high-energy radiation. Such environments are thought to be crucial in the early stages of planetary system development, as they contribute to the prebiotic compounds that later become part of interstellar dust clouds. Understanding how these materials evolve in different states provides insight into the chemical diversity of the galaxy. Future research on mapping the precise movement of gas within the nebula and determining whether external factors are influencing its evolution. If a binary companion is confirmed, it could provide further evidence that multiple star systems are a key factor in shaping structured nebulae. Long-term monitoring may reveal subtle shifts in brightness or morphology, indicating ongoing dynamic processes that have yet to be fully understood. If the central star eventually undergoes a supernova, it could transform the surrounding region by sending shock waves through the nebula, triggering secondary reactions and possibly altering its structure. The resulting supernova remnant would provide valuable data on how pre-existing mass loss affects the aftermath of stellar explosions. If a neutron star or black hole forms at the core, it may interact with the surrounding material in ways that produce additional high-energy emissions, making it a potential source of radio waves or X-ray bursts. The precision of the formation continues to challenge existing astrophysical models, suggesting that either previously unknown mechanisms are at work or that magnetic shaping plays a far greater role in stellar evolution than currently assumed. Upcoming telescopes with adaptive optics and interferometry will provide deeper insights into the processes governing the expansion of ionized gas and the interaction between radiation and dust within. While its ultimate fate remains uncertain, its significance as an astrophysical case study is undeniable. Whether it is a short-lived phase of stellar evolution or a long-standing feature that will persist for thousands of years, it represents a rare and valuable opportunity to study the forces that shape the most massive stars in the cosmos. The answers it holds could refine our understanding of how stars evolve, how they lose mass, and how they influence the galactic environment over cosmic timescales. The forces responsible for shaping this nebula remain a subject of debate, with multiple mechanisms potentially working in tandem to maintain its strikingly structured form. Dense circumstellar medium suggests that earlier mass ejection events may have interacted with surrounding material, creating shock fronts that reinforce the observed geometry. If stellar winds or episodic eruptions from the central star were directed by an unseen companion, their effects could have compounded over time, gradually sculpting the nebula into its current configuration. Magnetic fields are another possible factor influencing its development. In some high-energy astrophysical environments, magnetic pressure can guide ionized gas along preferred paths, constraining outflows into collimated jets or symmetric lobes. If this phenomenon is occurring here, it could help explain the sharp definition of the nebula's edges and the near-identical structure on opposite sides of the central star. Observations of other massive stellar remnants have shown that even weak magnetic fields can have a profound impact on outflow dynamics, reinforcing the idea that this nebula's shape may be magnetically driven. The chemical complexity of the surrounding gas adds another layer of intrigue. The discovery of molecular hydrogen and polycyclic aromatic hydrocarbons within the nebula suggests that the region has undergone prolonged exposure to ultraviolet radiation, leading to chemical reactions that produce complex organic compounds. If this material later becomes part of interstellar clouds, it could contribute to the formation of planets or even prebiotic chemistry in future stellar systems. This highlights the role of evolved stars not only as sources of heavy elements, but also as potential contributors to the early chemistry of planetary environments. The velocity distribution of ejected material is also a critical factor in understanding the formation of the nebula. If the gas is expanding uniformly, it would suggest that the star has been losing mass gradually over an extended period. However, if velocity gradients are detected, with some regions moving faster than others, it could indicate episodic bursts of energy, possibly linked to a hidden binary companion or internal stellar instability. High-resolution spectroscopic studies will help determine whether the structure has remained stable or if it is actively evolving, with changes in brightness or morphology providing additional clues. Comparisons to other known stellar outflows provide valuable context for interpreting this structure. The similarity to bipolar planetary nebulae, which are often shaped by binary interactions, suggests that the nebula may represent an earlier stage of this process in a much more massive system. If future observations confirm the presence of an orbiting companion, it could provide strong evidence that binarity is a key factor in the formation of highly structured nebulae, challenging existing models of single-star mass loss. The possibility that the central star is approaching a terminal supernova phase adds an additional layer of urgency to ongoing research. If this is a pre-supernova system, then the surrounding nebula may play a crucial role in determining the characteristics of the eventual explosion. A dense circumstellar medium could shape the supernova's light curve, producing an extended afterglow, or even influencing the type of remnant that forms. If the core collapse results in a neutron star or a black hole, the interaction between the compact object and the surrounding nebula could generate secondary emissions, including high-energy X-ray or radio bursts. Some researchers propose that this nebula represents a previously unrecognized category of structured stellar outflows, distinct from both planetary nebulae and classical supernova remnants. If so, it could mean that highly organized mass loss occurs in more stars than currently expected, but remains undetected in systems with less favorable viewing angles. Advanced three-dimensional modeling, combined with data from next-generation telescopes, will be necessary to determine whether similar formations exist elsewhere in the galaxy. Long-term monitoring will be essential to track any changes in the nebula structure. If subtle shifts in brightness or gas distribution are detected, it could indicate ongoing mass loss or dynamic interactions within the expanding material. Alternatively, if the nebula remains unchanged over decades of observation, it would suggest that its formation was driven by a past event rather than active processes occurring in the present. Either scenario will provide valuable insights into how massive stars shed their outer layers and how those layers evolve over time. The nebula's role in the broader astrophysical landscape extends beyond its immediate surroundings. If it is indeed an example of a structured pre-supernova outflow, it could help refine predictions for other massive stars end of their life cycles. Understanding the processes shaping this formation could improve models of how supernovae interact with their environments, potentially leading to better interpretations of historical supernova remnants observed throughout the galaxy. Future research will focus on uncovering the underlying drivers of the nebula's symmetry, whether they be magnetic forces, binary interactions, or unknown stellar dynamics. Upcoming missions and observational campaigns will provide increasingly detailed data, helping to answer fundamental questions about the role of evolved stars in shaping the structure of the interstellar medium. Regardless of what mechanisms are ultimately responsible, the nebula remains a rare and invaluable opportunity to study the complex interplay between stellar evolution, mass loss, and the physical forces that govern the cosmos. As observational techniques continue to improve, new details about this enigmatic formation will likely emerge, shedding light on the precise mechanisms responsible for its near-perfect symmetry. The role of radiation pressure in shaping the expanding gas is an area of active investigation, as intense stellar winds could be driving material outward along well-defined paths. If the star is emitting energy anisotropically, with stronger radiation in specific directions, it could be influencing the way ejected material disperses into space. This could help explain the structured nature of the nebula, particularly if interactions with a surrounding dust disk or magnetic field are reinforcing its geometric appearance. High-energy phenomena may also be contributing to the evolution of this structure. Some researchers suggest that the presence of shock fronts, regions where fast-moving gas collides with slower material, could be shaping the expanding nebula. These interactions create areas of increased density and ionization, altering how light scatters and giving the nebula its distinctive brightness distribution. If these shocks are being driven by periodic stellar outbursts, then the formation could be the result of multiple ejection events over time, each adding to the overall complexity of its structure. Infrared observations continue to provide new insights into the dust and gas composition of the surrounding environment. Data suggests that the dust grains within the nebula are relatively large compared to those found in diffuse interstellar clouds, possibly indicating that they have undergone significant processing due to radiation collisions. If this region is rich in carbon-based compounds, it could support the idea that evolved stars contribute not only to heavy element enrichment but also to the formation of molecular precursors essential for planetary system development. Determining the precise age of the nebula is another critical aspect of ongoing research. By analyzing the expansion velocity of different gas layers, astronomers aim to estimate when the initial mass ejection occurred. If the nebula is relatively young, it could be the result of a recent instability in the central star, whereas an older formation would suggest a more gradual mass loss process over an extended period. This distinction is important in understanding whether this structure is a transient phase that will evolve into a more diffuse remnant, or if it represents a long-lived phenomenon sustained by continuous energy input. The potential presence of a binary companion remains a crucial question, as its confirmation would provide a strong explanation for the nebula's ordered structure. If a secondary star is orbiting the central object, its gravitational influence could be directing material into specific flow patterns, producing the observed symmetry. Some models suggest that if a white dwarf, neutron star, or even a black hole is present, accretion-driven outflows could be responsible to striking shape. Identifying subtle variations in the motion of the primary star or detecting indirect signs of a hidden companion through X-ray or radio emissions may help resolve this mystery. Further study of the polarization of light from the nebula will be useful in determining whether magnetic forces are playing a significant role in its evolution. If light scattering patterns indicate the presence of aligned dust grains, it could suggest that a strong magnetic field is guiding the expansion of gas. Such a scenario would align with models of magnetically collimated outflows, which have been observed in other astrophysical environments, including young stellar objects and active galactic nuclei. One of the most intriguing possibilities is that this formation represents an early stage of a process that has not been widely documented in astrophysics. If it turns out to be a precursor to a more well-known structure, such as a planetary nebula or a supernova remnant, it could provide a unique opportunity to study how these phenomena develop over time. Observing how the nebula changes in the coming years will be crucial in determining its future trajectory, whether it will eventually dissipate into the interstellar medium or continue evolving into a more complex structure. If the central star ultimately undergoes a supernova, the surrounding material could play a key role in shaping the explosion's observable characteristics. The presence of dense circumstellar matter could cause significant interaction between the supernova shock wave and the pre-existing nebula, leading to an unusually bright and prolonged event. If this occurs, it could offer direct observational evidence of how mass loss influences the final stages of massive star evolution. Long-term monitoring with next-generation telescopes will be essential in answering the remaining questions surrounding this extraordinary structure. Instruments capable of resolving fine details in the gas distribution, magnetic field orientation, and spectral properties will provide the data needed to construct a more complete picture of its origins and evolution. If similar objects are identified elsewhere in the galaxy, it may indicate that these types of structured outflows are more common than currently believed, potentially leading to a re-evaluation of existing models of stellar mass loss. Regardless of its ultimate fate, this nebula remains one of the most visually striking and scientifically valuable examples of how complex forces interact in the late stages of stellar evolution. Whether shaped by binary dynamics, magnetic fields, episodic outbursts, or a combination of multiple factors. Its existence challenges conventional astrophysical theories and offers an unparalleled opportunity to study the intricate processes governing massive stars. Future observations will undoubtedly bring new discoveries, deepening our understanding of how these cosmic structures form, persist, and eventually transform into the next generation of celestial phenomena. As observations continue to refine our understanding of this extraordinary formation, the interplay between multiple astrophysical forces becomes increasingly apparent. The near-perfect symmetry suggests that a finely tuned combination of stellar winds, radiation pressure, gravitational dynamics, and possibly magnetic confinement is at work. Each of these factors contributes to shaping the expanding shell of gas and dust, maintaining its structural integrity over time. Whether this level of organization is an inherent property of certain types of stellar outflows or a rare coincidence of conditions remains an open question. Infrared spectroscopy has revealed variations in the temperature and density of different regions within the nebula, indicating that it is not a uniform shell, but rather a complex, layered structure. This suggests that multiple ejection events may have occurred at different times, each adding a new component to the overall formation. If past eruptions have been episodic, possibly regulated by internal instabilities in the central star or interactions with an orbiting companion, the nebula could be an evolving record of its progenitor's mass loss history. The detection of specific ionized elements in the surrounding gas suggests that high-energy radiation from the central star is actively altering its chemical composition. Regions exposed to the most intense ultraviolet and X-ray flux exhibit signs of ionization-driven molecular dissociation, while more shielded areas retain heavier molecules and dust grains. This dynamic environment provides insights into how massive stars influence their surroundings, gradually enriching the interstellar medium with elements forged in their interiors. One of the primary challenges in understanding the nature of this structure is determining whether its symmetry is a transient feature or a long-term characteristic. If it is the result of a recent outburst, it may slowly degrade over time as the expanding material interacts with external forces. On the other hand, if it is stabilized by ongoing processes, such as a sustained mass flow or a persistent magnetic field, its geometry may remain largely unchanged for thousands of years. Tracking subtle shifts in the nebula's brightness and morphology over successive observational periods will be essential in distinguishing between these possibilities. Comparisons to other known examples of structured nebulae suggest that ordered mass ejections are more common than previously assumed. However, the degree of symmetry observed here is exceptionally rare, indicating that specific conditions must be met for such formations to arise. If future surveys identify similar objects in different regions of the galaxy, it could provide a broader statistical foundation for understanding how often these structures occur and what factors contribute to their development. Advanced numerical simulations are being used to model the potential formation scenarios for this system. By incorporating variables such as stellar rotation, pulsation-driven mass loss, and binary interactions, researchers hope to replicate the observed structure and determine which force evolution. Early results suggest that a combination of rapid stellar and a companion's gravitational influence could create flow patterns that resemble the nebula's distinct shape. If these models prove accurate, they could offer a new perspective on the role of binarity in shaping circumstellar environments. Another intriguing aspect is the potential for future variability in the central star itself. If it is nearing the end of its evolutionary cycle, further instability may lead to additional mass ejections or luminosity fluctuations. Such changes could provide direct observational evidence of how the formation is being influenced by ongoing stellar processes. If a sudden brightening event occurs, it could be a sign of an impending transformation, possibly signaling the transition into a Wolf-Rayet phase or even the approach of a terminal explosion. If the star ultimately undergoes a core collapse supernova, the surrounding nebula could play a critical role in shaping the aftermath. A dense pre-existing medium could result in an unusually energetic explosion, with shock waves producing intricate interaction patterns within the already structured outflows. Such an event would be a rare opportunity to observe how massive stars influence their own supernova environments, offering insights into the processes that govern the final state stages of stellar life. Long-term monitoring efforts will focus on detecting changes in expansion velocity, ionization levels, and thermal emissions within the nebula. Any deviations from the expected behavior could indicate pre-known influences at work, potentially revealing new physics governing stellar outflows. With upcoming space-based and ground-based observatories providing increasingly detailed data, a clearer picture of this remarkable formation will continue to emerge. Whether this structure is an exceptional case or part of a broader, yet underappreciated category of organized mass ejections, its study is reshaping perspectives on how stars interact with their surroundings. The precise forces maintaining its near-perfect symmetry remain one of the most compelling mysteries in modern astrophysics, and future discoveries may provide the missing pieces needed to unlock its true nature. Regardless of what new revelations come to light, this nebula stands as a striking testament to the complex and often unexpected beauty of stellar evolution. The persistence of such a structured formation raises fundamental questions about the longevity of ordered nebulae and the mechanisms that sustain their geometry over time. If the observed symmetry is not merely a transient effect, then ongoing processes must be actively maintaining its precise form. One possibility is that the radiation pressure from the central star is continually shaping the expanding gas, reinforcing existing structures and preventing dissipation. In this case, variations in stellar output could lead to subtle but measurable shifts in the nebula's morphology, offering insights into how radiation-driven mass loss influences circumstellar environments. The presence of complex molecular compounds within the expanding shell suggests that chemical evolution is occurring on a large scale. As ultraviolet and X-ray radiation interacts with dust and gas, it triggers photodissociation processes that break apart existing molecules and encourage the formation of new ones. This cycle of destruction and recombination is key to understanding how massive stars can contribute to the molecular diversity of interstellar space. If the conditions within the nebula are enough, the gradual synthesis of increasingly complex compounds, further enriching the surrounding medium. Velocity mapping of the nebula's outflows is another avenue of investigation that may yield crucial insights into its formation history. If different layers of gas are expanding at distinct rates, it could suggest multiple episodes of mass ejection, each contributing to the overall structure. By reconstructing the motion of individual gas clouds within the nebula, astronomers can determine whether the expansion is accelerating, slowing down, or maintaining a steady rate. A uniform velocity distribution would support the idea of a single, well-coordinated outflow event, while irregularities could indicate ongoing dynamic interactions between different layers of material. The role of external influences, such as interactions with the surrounding interstellar medium, is also worth exploring. If the expanding nebula is encountering regions of higher density gas, it could be experiencing external pressure that helps define its shape. This scenario is particularly intriguing because it would imply that the large-scale structure of the interstellar medium plays an active role in shaping stellar remnants. If such interactions are confirmed, they could offer a broader context for understanding how similar nebulae form across different galactic environments. Advances in computational astrophysics are enabling the development of increasingly sophisticated simulations that attempt to recreate the conditions necessary for such a structured formation. These models incorporate factors such as stellar rotation, magnetic field dynamics, radiation transport, and binary gravitational effects. The goal is to determine whether a single dominant force is responsible for shaping the nebula, or if multiple factors are working together in a complex interplay. Early results suggest that while radiation pressure and magnetic fields alone can produce organized outflows, the addition of a binary companion significantly enhances the likelihood of maintaining long-term symmetry. If a compact object is present within the system, it could further complicate the dynamics of the nebula. A neutron star or black hole companion could be influencing the surrounding material through accretion-driven winds or relativistic jets. These high-energy processes could create additional structure within the nebula, potentially explaining regions of enhanced brightness or density variations observed in different wavelengths. If future observations detect X-ray emissions or rapid fluctuations in radio signals, it may provide direct evidence of a compact remnant playing an active role in the system. Another aspect of interest is whether this nebula represents a unique evolutionary path or if it shares characteristics with other known structures that have been observed at different stages of development. If similar formations exist but have gone unnoticed due to unfavorable viewing angles, it could suggest that such ordered mass ejections are more common than previously thought. A systematic survey of structured nebulae using high-resolution telescopes could help identify additional examples, refining our understanding of the conditions necessary for their formation. The long-term future of the nebula remains uncertain, as its fate will largely depend on the evolution of its central star. If the star continues shedding mass at a steady rate, the surrounding structure may gradually expand and fade over thousands of years, blending into the interstellar medium. Alternatively, if the star undergoes a more dramatic transition, such as collapsing into a white dwarf, neutron star, or black hole, it could leave behind a compact remnant that continues to interact with the surrounding material. If this leads to periodic bursts of energy, the nebula may experience episodic reillumination, creating a variable emission profile that persists long after the initial mass ejection event. If a supernova does occur within the nebula, it could produce one of the most visually and scientifically interesting explosion remnants ever observed. The pre-existing structure would shape the way the supernova shockwave propagates, creating intricate patterns of glowing filaments and ionized gas. The resulting explosion could provide valuable data on how mass loss before core collapse affects the properties of the supernova itself, offering a real-world test case for theoretical models of stellar death. Regardless of its ultimate fate, this nebula remains an astrophysical anomaly that continues to challenge conventional understanding. Its striking symmetry, dynamic environment, and potential connection to high-energy astrophysical processes make it an ideal subject for continued study. The combination of observational data, theoretical modeling, and future technological advancements promises to unlock further insights into the mechanisms responsible for shaping such extraordinary cosmic structures. In the broader context of stellar evolution, this nebula highlights the diversity of pathways that massive stars can take as they approach the end of their life cycles. Whether it represents a transient phenomenon or a more persistent stage of mass loss, it serves as a reminder that the processes governing the formation and evolution of stellar remnants are more intricate than previously assumed. As research continues, each new discovery will bring us closer to understanding the fundamental forces that sculpt the universe's most fascinating and mysterious celestial objects. As more data is gathered, the intricate dynamics governing this structured outflow become clearer, yet many aspects remain elusive. The balance between stellar wind pressure, radiation forces, and gravitational interactions is delicate, and minor fluctuations in any of these variables could significantly alter the nebula's morphology over time. If its current shape is maintained for an extended period, it would suggest an ongoing regulating mechanism, possibly a combination of persistent mass loss cycles and external constraints imposed by either a magnetic field or a binary companion. A deeper understanding of the internal motion of the gas is crucial in deciphering the structure is static. If gas and dust are flowing outward at a uniform velocity, then the nebula is expanding symmetrically without significant turbulence. However, within the outflow exhibit differences in acceleration, individual processes are acting simultaneously. The presence of high-velocity, for example, could point to localized shock waves where ejected material interacts with remnants of previous steps. If the star at the center is rotating rapidly, it could also be affecting the mass ejection pattern. Fast rotation alters the shape of the stellar atmosphere, making it more oblate and enhancing equatorial mass loss through centrifugal forces. This would naturally produce an extended disk or toroidal structure around the star, which could act as a guiding framework for the broader nebula. If rotation is a key factor, then future spectroscopic studies of the star's surface may reveal Doppler broadening effects, indicating differential velocity regions across its surface. The role of ionization fronts within the nebula is another aspect of interest. If the central star's radiation is continuously exciting the surrounding gas, it may be forming stratified layers where different elements are ionized at varying depths. This would lead to a multi-tiered composition where hydrogen, helium, oxygen, and heavier elements are distributed according to their ionization potentials. Understanding these ionization boundaries could provide insight into how far the star's influence extends and whether the outer regions of the nebula are still actively shaped by radiation or are merely residual structures from past eruptions. The possible presence of dust filaments or molecular clouds within the nebula suggests that complex interactions between gas phase elements and solid particles are occurring. Dust grains play an important role in astrophysical chemistry, acting as catalysts for molecule formation by providing surfaces where atomic interactions can take place more efficiently. If the nebula is rich in carbonaceous or silicate dust, it may indicate that material from the star is condensing into solid form, eventually contributing to the raw material for future planetary system formation. One key observational goal is to determine whether the nebula is optically thick or if it allows significant amounts of radiation to escape. If it is largely transparent at certain wavelengths, then light from the central star may be escaping in directed beams, influencing surrounding interstellar clouds beyond the immediate boundaries of the structure. This could result in faint emission regions detectable in infrared or radio wavelengths, providing clues about how the nebula interacts with the broader galactic environment. The possibility of a faint, extended halo surrounding the main structure is also being explored. Some nebulae exhibit diffuse outer layers, where lower density gas gradually transitions into the surrounding medium. If this system follows a similar pattern, then it may have an extended outer envelope that is not immediately visible in current observations but could be revealed through deep exposure imaging techniques. If such a halo is present, it may contain older material from earlier mass ejections, offering a more complete picture of the star's long-term evolution. Further study of light polarization within the nebula may also help in determining whether magnetic fields are contributing to its structure. If dust grains are aligned along a preferred axis, it could indicate that an underlying magnetic field is shaping the flow of ionized gas. Strong magnetic confinement could explain why material appears to be expanding in a highly organized manner rather than dissipating irregularly, as is typical in many other stellar outflows. High-resolution radio observations could provide additional evidence of magnetic influence by detecting synchrotron radiation, which occurs when charged particles spiral along magnetic field lines. The long-term monitoring of the nebula's brightness and shape will provide important clues about its future evolution. If no significant changes are observed over the coming decades, it could suggest that the system has reached a stable equilibrium, where forces acting within it counterbalance one another. However, if gradual shifts in emission intensity or structural features are detected, it may indicate that the nebula is still undergoing active reshaping, driven either by continued mass loss or external forces acting on the expanding shell. If the central star eventually transitions into a late-stage degenerate remnant, such as a white dwarf or neutron star, its interactions with the nebula may take on new characteristics. A cooling white dwarf would emit lower energy radiation, potentially altering the ionization structure of the nebula over time. If a neutron star or black hole forms, accretion of remaining material could generate episodic bursts of high-energy emissions, further complicating the evolutionary trajectory of the surrounding gas. With the advent of more sensitive astronomical instruments, including future space-based and ground-based telescopes, finer details of the nebula's composition and kinematics will become accessible. Multi-wavelength campaign radio, and X-ray data will allow researchers to construct an increasingly refined model of the processes governing this remarkable structure. By extending observational coverage to different regions of the electromagnetic spectrum, new physical interactions may be revealed, providing additional pieces to the puzzle of its formation and persistence. Understanding this nebula has broader implications beyond its immediate structure. If similar objects are discovered in different star-forming regions or near other evolved stellar systems, it could indicate that such formations represent a recurring phase in the life cycles of massive stars. This would provide new constraints on theories of stellar mass loss and the role of binarity, magnetic fields, and radiation pressure in shaping astrophysical outflows. Each discovery would bring us closer to understanding the universal principles that govern the transformation of stars and the lasting impact they leave on their environments. As research continues, the nebula remains a fascinating subject at the intersection of multiple astrophysical disciplines. Its structured appearance challenges traditional models, suggesting that either previously unrecognized mechanisms are at work or that known processes are operating in a more complex manner than currently understood. The insights gained from this system will not only refine our understanding of mass loss in evolved stars but may also influence broader concepts in astrophysics, from supernova progenitors to the formation of chemically enriched regions within galaxies. No matter what future observations reveal, this nebula stands as a striking testament to the intricate and often unexpected interactions that shape the cosmos. The persistence of such an intricate and symmetrical structure suggests that it is not merely a fleeting but a system governed by sustained forces. If the nebula were purely the result of a single explosive event, its features would have begun to dissipate in a more chaotic fashion over time. Instead, the defined edges and organized outflows indicate that ongoing mechanisms are reinforcing its structure, preventing it from dissolving into an irregular cloud. Understanding the nature of these stabilizing forces will provide crucial insights into how long such formations can persist and what role they play in the broader galactic ecosystem. One of the key aspects under investigation is whether the gas and dust within the nebula are interacting with interstellar magnetic fields beyond the immediate influence of the central star. If so, the entire system may be embedded within a larger scale magnetized region that is influencing is distributed. This would mean that its shape is not solely the result of internal stellar processes, but is also being conditioned by environmental factors on a much larger scale. The interaction of expanding nebulae with the ambient galactic magnetic field is a relatively unexplored area of research, but it could have profound implications for understanding the formation of structured outflows in other astrophysical settings. The possibility that the nebula is part of a larger feedback loop within its local stellar neighborhood is another avenue of study. If mass loss from the central star is feeding surrounding molecular clouds, it could be triggering secondary star formation in nearby regions. In this scenario, the nebula is not just a byproduct of stellar evolution but an active participant in the recycling of matter, enriching the interstellar medium with heavier elements and influencing the next generation of star formation. If observations detect enhanced star-forming activity in adjacent regions, it would support the idea that evolved stars contribute more directly to galactic chemical evolution than previously assumed. Infrared imaging continues to reveal variations in dust grain size and composition, suggesting that material within the nebula is undergoing active processing. Some regions appear to contain larger, more complex carbonaceous compounds, possibly formed through prolonged exposure to ultraviolet radiation. If dust grains within the nebula have been altered by repeated ionization cycles, they may exhibit unique spectral signatures that could serve as a marker for similar objects elsewhere in the galaxy. By identifying the specific types of molecules present, researchers may be able to determine whether this environment is conducive to the formation of organic precursors to planetary systems. The thermal structure of the nebula is another critical factor in assessing its long-term stability. If the gas within it is being heated unevenly, localized instabilities may form, leading to subtle structural changes over time. High-resolution temperature maps created from multi-wavelength observations could reveal whether certain regions are cooling more rapidly than others, potentially setting the stage for future condensation of material. If dense clumps are forming within the nebula, they could eventually collapse under their own gravity, leading to the formation of new stellar objects. While this would be an unexpected outcome for a system of this type, it cannot yet be ruled out. The search for variability in the brightness of the central star remains ongoing. If the star exhibits periodic fluctuations in luminosity, it may indicate pulsational instabilities affecting its outer layers. These variations could, in turn, influence the mass loss rate, leading to episodic enhancements in the nebula structure. If brightness changes are detected, correlating them with observed changes in the nebula's emission patterns could help establish a direct link between stellar activity and the evolution of the surrounding material. The outermost layers of the nebula are of particular interest, as they may provide a record of its earliest formation stages. If weak shock waves are detected propagating through the outer edges, it could suggest that the nebula is still expanding into previously undisturbed interstellar space. These shocks could be producing low-density filaments that are difficult to detect in optical wavelengths but may be revealed through radio observations. If such features are confirmed, they would provide valuable clues about the nebula's expansion dynamics and whether it is still actively interacting with its environment. One of the most significant remaining uncertainties is whether this structure represents a phase that other massive stars undergo or if it is an exceptional case. If similar objects exist but have not yet been identified, it could mean that such nebulae are more common than previously thought but remain undetected due to observational limitations. Systematic searches using next-generation telescopes with enhanced sensitivity in the infrared and radio bands may reveal whether this is part of a broader class of stellar outflows that have gone largely unrecognized. If the nebula is indeed a precursor to a supernova event, its surrounding structure may serve as a unique observational target when the explosion occurs. The interaction between the supernova shockwave and the pre-existing circumstellar material could produce intricate patterns of emission, allowing astronomers to witness the complex interplay of stellar remnants and nebular evolution in real time. The ability to study such an event would provide unprecedented insights into how mass loss influences the properties of supernova explosions, helping to refine models of core collapse dynamics. The continuing refinement of astrophysical models incorporating observational data from this nebula will lead to a better understanding of the forces shaping high-mass stellar environments. As computational capabilities advance, simulations will be able to incorporate increasingly detailed physical parameters, allowing researchers to test different formation scenarios and compare them directly to observational data. A definitive explanation for the nebula structure emerges. It will not be the most intriguing astrophysical mysteries but also provide a framework for understanding similar objects that may be discovered in the future. Regardless of what new findings emerge, this nebula remains a compelling example of the complexity of stellar evolution and the diversity of structures that can arise from seemingly chaotic processes. Its continued study will provide valuable insights into how stars interact with their surroundings, how mass is redistributed throughout the galaxy, and how the final stages of stellar evolution shape the interstellar medium. Each new observation brings us closer to uncovering the full story of this remarkable formation, revealing the intricate and often unexpected ways in which stars leave their mark on the cosmos. As research progresses, the long-term evolution of this nebula remains one of the most compelling unknowns. Whether its structure will remain stable for thousands of years or gradually dissipate into the surrounding interstellar medium is still unclear. If the forces maintaining its symmetry weaken over time, the well-defined edges may begin to blur as expanding gas disperses. However, if there are persistent shaping mechanisms, such as ongoing stellar mass loss, magnetic field interactions, or external pressure from surrounding interstellar clouds, the structure may remain largely intact for an extended period. Observations in multiple wavelengths continue to refine our understanding of the nebula's internal structure. Radio observations, for instance, are particularly useful in detecting cold gas components that may not be visible in optical or infrared light. If significant amounts of molecular gas are present, it could indicate that the outer layers of the nebula are cooling and condensing or localized high-density regions. These structures, would evident interaction and the surrounding environment. The distribution of heavier elements within the nebula interest. Materials, nitrogen, and carbon are concentrated in specific regions. It could suggest that differing at different rates or that ionization fronts are influencing chemical processes. Detailed spectral analysis made these out in earlier nuclear fusion particles within the central star or if they are the result of more recent nucleosynthesis in an unstable stellar atmosphere is determining whether it is interacting with external gas flows from other nearby stellar sources. If the region around the nebula contains additional massive studding, could be influencing the expansion structure. This would suggest that nebular symmetry is not solely dictated of the selected environment. Interactions are detected, they could provide into how massive stars shape their surroundings on a larger scale. The question of whether the central star is truly alone remains unresolved. The possible unseen binary companion can be explored through precise radial velocity measurements and high-resolution imaging. If a compact object, such as a neutron star or white dwarf, is orbiting within the system, its gravitational effects could be contributing to the organized shape of the surrounding material. Scenario mass ejection events, which would be consistent with the layered appearance of some regions within the nebula. The structure with thick magnetic fields is another factor under examination. If the nebula's shape is influenced by scale actions, it is not an isolated phenomenon, but part of a broader network of interconnected astrophysical processes. If future measurements detect signs of external magnetic influence, it may support the idea that structured stellar outflows are not solely dictated by internal dynamics, but can be modified by extrinsic forces acting on a galactic scale. If this nebula does eventually undergo a transformation due to a supernova explosion, the resulting remnant could provide a rare opportunity to observe how a pre-existing structured outflow interacts with a high-energy shock wave. Such an event would likely produce an asymmetric supernova remnant, with expanding material encountering dense regions in some directions while escaping more freely in others. This would create a highly complex emission pattern, providing valuable data on how circumstellar matter influences the outcome of core collapse events. Even if a supernova does not occur in the near future, the nebula's gradual evolution will offer important insights into how mass loss continues in late-stage stellar systems. Long-term observations will track changes in its brightness, expansion rate, and spectral properties, revealing whether the structure is gradually dispersing or if it remains dynamically active. If the nebula continues to exhibit stability over time, it may challenge existing theories of mass ejection and suggest that previously unrecognized stabilizing mechanisms are at work. Future telescopes, particularly those designed for high-resolution spectroscopy and polarization studies, will be instrumental in unraveling the finer details of the nebula's composition and motion. By studying variations in emission across different regions, astronomers determine whether specific forces, such as localized shock waves or radiation pressure differences, are its evolution. These observations will help build a more comprehensive model of how massive stellar outflows develop and persist. This nebula remains a remarkable case study for astrophysics, not only because of its striking appearance but because of the numerous unanswered questions surrounding its origin, stability, and eventual fate. Whether it represents a rare phenomenon or an overlooked stage in stellar evolution, it challenges conventional assumptions and invites further exploration into the complexities of massive star systems. Each new observation brings us closer to a full understanding of the forces shaping the cosmos, demonstrating that even in an era of advanced astronomical technology, the universe continues to reveal mysteries that push the boundaries of human knowledge. As the study of this advances, its significance extends beyond its immediate formation, hinting at broader astrophysical processes that govern the life cycles of massive stars. The stability of its shape's mass ejection is occurring in a controlled manner, possibly influenced by a combination of radiation pressure, rotational effects, and external constraints imposed by a larger galactic framework. The degree to which these forces interact remains an open question, but each new observational dataset refines our understanding of the mechanisms at play. Recent spectroscopic measurements have revealed variations in ionization levels across different regions of the nebula, suggesting that the central star's radiation is not evenly distributed. This could indicate that the star is experiencing rotationally modulated emissions, where different parts of its surface emit varying intensities of ultraviolet and X-ray radiation over time. If so, the asymmetry in radiation output could be influencing the density distribution of surrounding, enforcing the star preferentially ionizing certain areas while leaving others relatively undisturbed. The search for a binary companion remains an ongoing effort, with continued radial velocity studies and high-resolution campaigns aiming to detect any subtle gravitances that might suggest the presence of an orbiting secondary object. If a compact remnant, such as a neutron star dwarf, is hidden within the system, it could be driving periodic through mass transfer interactions. No direct evidence of a secondary star, the possibility of past interactions with a companion remains a plausible for the structured ejection pattern. Magnetohydrodynamic modeling that if magnetic fields are present within the nebula, they could be acting as a stabilizing force, guiding ionized plasma along specific paths and preventing the structure from dispersing chaotically. If confirmed, provide new insights into magnetic configurations contribute of highly organized stellar remnants. Future polarization studies will be determining whether aligned dust grains or synchrotron emission signatures indicate the presence of magnetic shaping. The discovery of molecular compound regions of the nebula provides further evidence of ongoing chemical evolution. The identification of carbon-rich molecules, possibly including complex organics such as polycyclic aromatic hydrocarbons, suggests that the nebula is not simply a passive stellar remnant but a dynamic chemical environment where high-energy radiation is continuously altering molecular structures. This for the study of interstellar medium enrichment. As such, nebulae may act as sources of prebiotic material that eventually contribute to the formation of planetary systems. Another under examination is the thermal structure of the gas and dust within the nebula. If temperature gradients are detected, it could indicate localized heating effects caused by shocks or regions where high-energy radiation is penetrating deeper layers. By mapping these temperature variation spectral bands, astronomers can better understand whether the nebula is undergoing a cooling process or if certain regions are being repeatedly reheated by influences. Long-term monitoring efforts aim to determine whether the nebula exhibits subtle changes over time. If small-scale shifts in brightness or morphology are detected, they could signal ongoing interactions with external gas clouds or internal stellar variability influencing the surrounding material. If, on the other hand, the structure remains largely unchanged for decades, it would imply that the forces maintaining its shape are remarkably stable, challenging traditional models of nebular evolution. The broader implications of this research extend to the study of massive star populations in different galactic environments. If similar structured nebulae are discovered elsewhere, it would suggest that this is not an isolated phenomenon, but rather a recurring phase in the relation of certain types. Systematic surveys using telescopes could reveal whether holes exist, providing stimulants to theoretical frameworks. If this nebula eventually transitions into a supernova remnant, it will provide a unique opportunity to observe how circumstellar medium interacts with an energetic explosion. The resulting supernova shockwave would propagate through the pre-existing outflows, creating intricate emission patterns and potentially leading to asymmetric expansion dynamics. Such an event would be invaluable for refining models of core collapse supernovae and their surrounding material. Of its future trajectory, this nebula remains one of the most astrophysical puzzles of recent times. Its highly ordered structure defies conventional expectations, prompting a re-evaluation of the processes governing stellar mass loss and outflow organization. Whether shaped primarily by binary interactions, magnetic confinement, radiation-driven winds, or a combination of multiple forces, it offers an unparalleled opportunity to study the interplay between stellar evolution and dynamics. The continued investigation of this system will contribute to a deeper understanding of the fundamental principles that shape celestial structures, from the smallest dust grains to the largest formations. Each discovery adds another layer to our understanding of the cosmos, demonstrating that even in an era of observational capabilities, nature continues to surprise and challenge our theoretical frameworks. The nebula remains a beacon of scientific curiosity, inviting further exploration into the hidden mechanisms that govern the life and death of stars across the universe. As research into this remarkable nebula advances, it continues to serve as a key astrophysical laboratory, revealing the interplay of multiple forces that govern the evolution of massive stars. Its near-perfect symmetry, long-term stability, and complex chemical composition challenge traditional models of stellar mass loss and nebular dynamics. While most nebulae form through chaotic processes, this structure suggests a level of organization that is difficult to explain through standard mechanisms alone. The persistence of its shape implies that self-regulating forces must be at work, reinforcing its geometry over time and preventing it from dissipating into an amorphous cloud. One of the most intriguing aspects of this system is its potential connection to broader astrophysical phenomena. If the nebula is shaped by a previously unknown feedback mechanism, it could offer insights into how large-scale magnetic fields, binary interactions, and stellar wind collisions contribute to nebular evolution. Some researchers propose that if the star is rotating at high speeds, the centrifugal forces could be influencing the way material is expelled, leading to an anisotropic outflow pattern. This could explain why mass ejections appear to be funneled along specific axes rather than expanding spherically, as is common in many evolved stellar systems. Infrared studies have revealed that the dust composition within the nebula is not uniform, with certain regions showing enhanced concentrations of complex molecules. This suggests that the nebula is not only a passive structure but an active site of chemical evolution, where high-energy radiation is triggering reactions that modify the molecular landscape over time. The detection of carbon-based compounds, including large polycyclic aromatic hydrocarbons, PAHs, hints at a potential connection between nebular environments and the formation of prebiotic molecules in space. If the conditions within the nebulae found in protoplanetary disks, it could provide clues about the earliest stages of planetary system formation and how organic material is distributed across the galaxy. Another avenue of investigation involves mapping the expansion rate of the nebula's outer layers. If the velocity of the gas varies across different regions, it could suggest that multiple mass ejection events occurred at different times, each contributing to the layered structure. By analyzing Doppler shifts in the spectral lines of ionized gas, astronomers can reconstruct the three-dimensional motion of material within the nebula, determining whether it is undergoing uniform expansion or if internal forces are modifying its trajectory. If deviations from standard expansion models are detected, it could provide evidence for ongoing interactions with an unseen companion or an external pressure source shaping the outflow. The possibility that the nebula is part of a larger-scale galactic structure is also being explored. Surrounding region remnants of past stellar activity, it could indicate that the system is embedded within a dense stellar cluster, where multiple massive stars have contributed to shaping the environment. In this case, the nebula may not be an isolated formation but part of interconnected astrophysical processes, where different stellar outflows have created complex patterns of gas and dust. Detecting such connections could provide valuable insights into how massive stars collectively influence the structure of their host galaxies, contributing to the enrichment of interstellar space with heavier elements and driving the formation of new stars. Another critical is whether the nebula is in a stable or transitional. If it remains unchanged over long periods, it would suggest that the forces shaping it are self-sustaining, maintaining its geometry over extended timescales. However, if subtle shifts in brightness or morphology are observed, it could indicate that the nebula is evolving dynamically, either through continued interactions with its central star or through gradual dispersion into the interstellar medium. Monitoring these changes over time will help determine whether the nebula is a long-lived phenomenon or if it represents a fleeting stage in the late progenitor. If a supernova were to occur within the nebula, it would provide an unprecedented opportunity to study how an explosion propagates through a highly structured circumstellar medium. Unlike typical supernova remnants, which often expand into relatively diffuse environments, this system is a complex pre-existing structure that could dramatically influence the resulting shockwave dynamics. The interaction between the explosion and the nebula could lead to asymmetric ejective patterns, unusual light curves, or the formation of elementary structure. Ionized gas collides with winds of dust. such an observed in real-time data on how massive stars and their surrounding environments shape the final stages of their evolution. The presence of strong magnetic fields within the nebula remains an open question, but if confirmed, it could provide a crucial missing piece in exploring. If the expelled gas is interacting with an external magnetized region, it could be following field lines that dictate its alignment. High-resolution studies will be essential in determining whether the observed symmetry is the result of magnetic confinement, offering new insight. Scale cosmic magnetic fields influence nebular dynamics. The future of this nebula will involve deeper investigations into its chemical composition, velocity distribution, and interactions with its surrounding environment. Advanced instruments such as the James Webb JWST, Extremely Large Telescope, ELT, Atacama Large Millimeter Array, ALMA, will allow astronomers to probe deeper into its molecular and atomic structure, revealing details that were previously beyond the reach of observational technology. By combining data from multiple wavelengths, from radio to X-ray, reasonable to construct a comprehensive model of the nebula's evolution, identifying the forces responsible for its formation and its long-term fate. Remains one of the most examples of how stellar mass loss can create structures in space. Whether its symmetry is the result of binary dynamics, magnetic shaping, radiation pressure, or a combination of these factors, its existence challenges conventional theories of how with their surroundings. If it is part of a broader nebulae that have yet to be fully recognized, revision of current models highlighting previously unaccounted for processes that influence the final stages of a star's life. Regardless of what future discoveries reveal, this nebula stands as a striking example of the complexity of astrophysical systems. It demonstrates that even in an era of highly advanced astronomical technology, nature can present puzzles that defy easy explanation. Its study will not only deepen understanding of individual stellar outflows but also broader perspective on how stars shape they inhabit. Observation brings us one step closer to unraveling the mystery of formation, reinforcing the idea that the cosmos is far more intricate and dynamic than we ever imagined. As our understanding of this enigmatic nebula deepens, it becomes increasingly clear that its significance extends beyond a single region. Testament to the intricate forces governing stellar evolution, challenging existing theories and prompting new questions about how massive stars interact with their surroundings. Whether its structure is the result of binary interactions, magnetic shaping, radiation-driven or an interplay of multiple forces, it represents a rare and invaluable case study in astrophysics. The future of research into this system will rely on a combination of observational advancements. With the next generation of telescopes, including the James Webb Space Telescope, JWST, the Extremely Large Telescope, ELT, the Square Kilometer Array, SKA, and future X-ray observatories, astronomers will be able to probe deeper into the nebula's chemical composition, velocity distribution, and potential magnetic fields. High-resolution polarization studies will determine whether extrinsic influences are shaping its structure. Multi-wavelength spectroscopy will refine our understanding of its thermal dynamics and molecular complexity. If variations in brightness, expansion rates, or eye levels are detected over time, they could provide key evidence of ongoing interactions within the system. Another avenue of exploration lies in the search for similar objects elsewhere in the galaxy. If other nebulae with comparable symmetry are discovered, it could indicate that this is not a unique and part of a broader, yet previously unknown class of stellar outflows. Systematic surveys and imaging techniques may uncover additional examples, helping to establish the conditions necessary for such formations to occur. If no other similar structures are found, it will reinforce the exceptional nature of this nebula, making it a priority for continued study. Long-term monitoring will also be essential in determining the nebula's ultimate fate. If it remains stable over centuries, it would suggest that the forces maintaining its shape are self-sustaining, potentially revealing new physics governing mass loss in evolved stars. However, if it begins to change, whether through gradual dissipation with the interstellar medium, or the influence of an external shockwave, it may provide a rare opportunity to witness a transitionary phase in the evolution of a stellar remnant. If a supernova occurs within this structure, the resulting shockwave could interact with the pre-existing nebula in a way that has never been observed before, offering unprecedented insights into how massive stars shape their surroundings both before and after their explosive deaths. Ultimately, this nebula serves as a reminder that even in an age of advanced astronomical instrumentation and sophisticated theoretical models, the universe still holds mysteries that defy easy explanation. It is a challenge to our understanding of stellar physics, a catalyst for new discoveries, and a window into the complex and dynamic processes that shape the cosmos. As technology advances and new data become available, each observation brings us closer to unlocking the full story behind this extraordinary formation, ensuring that its legacy will endure as one of the most intriguing astrophysical puzzles of our time. Whether it remains a stable, structured beacon in the cosmos or transforms dramatically in the coming centuries, its study will continue to inspire curiosity, push the boundaries of astrophysical research, and expand our knowledge of the fundamental forces that govern the universe. The Antennae galaxies, also known as NGC 4038 and NGC 4039, represent one of the most stunning examples of galactic interaction ever observed. These twin celestial entities, engaged in an intricate cosmic dance, fascinated astronomers and enthusiasts alike for centuries. Their remarkable structure, shaped by powerful gravitational forces, chaotic beauty emerging when galaxies collide and merge over millions of years. Often referred to as cosmic antennae, this pair lies approximately 60 million light-year constellation Corvus. Originally separate spiral galaxies currently experience a captive process, generating stellar phenomena. Their elongated tidal tails, from which the antennae derive their distinctive name, extend far, filled with gas, dust, and stars expelled during their gravitational encounter. What makes this celestial pair even more intriguing is its role as a cosmic laboratory. Within their turbulent interior, astronomers have identified regions of vigorous star formation known as Transients. These stellar nurseries, and dust compressed during the collision, produce stars at a rate significantly surpassing typical cycles. Studying this entwined system enables researchers to better comprehend galaxy formation and evolution, revealing fundamental processes shaping the universe. The detailed structure of the race is not only visual but scientifically precise. Observations from the Hubble Space Telescope and other advanced observatories have unveiled intricate features within individual star clusters. Some of these clusters rank among the most massive and luminous ever recorded, containing packed into packed regions. These findings offer astronomers insights into environments similar to the early when galactic mergers occurred more frequently. As these interwoven spirals continue their prolonged collision, gravitational forces trigger impressive phenomena. Massive clouds of molecular gas become compressed, igniting the formation of hot, young stars. These stars emit intense ultraviolet radiation, stellar winds, shaping the surrounding interstellar medium and sustaining cycles of structure. The dynamic interplay between gravity, radiation, and stellar winds generates a continuously evolving cosmic landscape, highlighting the universe's immense complexity. This celestial collision also provides a preview of the distant future of the galaxy. Astronomers anticipate a similar encounter between the Milky Andromeda galaxy in approximately 4 billion years. Interaction. Scientists gain valuable knowledge about future in our galactic neighborhood. Although galaxy mergers are not rare occurrences, the antennae offer an exceptionally vivid illustration of their transformative impact. The gravitational ballet of these interacting galaxies serves as a powerful, immense forces governing the cosmos. These two celestial companions, once separate entities with distinct identities, are merging into a unified structure. Though their encounter appears violent and chaotic, this action ultimately creates a new galaxy, enriched by the remnants of its predecessors. This galactic fusion exhibits the universe's extraordinary capacity for both destruction and creation, dismantling old formations to give rise to new cosmic wonders. The interacting pair has long captured the attention of astronomers studying multi-wavelength astronomy. Observation electromagnetic spectrum, from radio waves to X-rays, have uncovered aspects of their intricate interaction. For example, X-ray analyses have revealed the existence of supermassive black holes at the center of each galaxy, as well as hot gas energized by solar winds. These energetic phenomena offer valuable insights into the physical processes at work during galaxy collisions. Beyond the importance, this cosmic duo inspires awe and wonder worldwide. Striking images captured by powerful telescopes have become iconic representations of the universe's profound beauty. Their expansive hills and vibrant starburst regions evoke curiosity, reminding us of the vast mysteries existing beyond our home planet. Continuing research into these merging galaxies constantly pushes the boundaries of our understanding. As observational technologies evolve, astronomers will explore this remarkable pair in even greater detail, providing new insights into the dynamics of galaxy mergers and cosmic evolution. This celestial pair thus stands as a powerful testament to humanity's ongoing scientific pursuit and the endless potential for discovery in the universe. The eternal embrace of these colliding giants narrates a captivating story of transformation and cosmic renewal. It reveals the immense gravitational forces shaping the universe, depicting stars forming, evolving, and eventually dying as galaxies transform over billions of years. By investigating these galaxies, we gain deeper insight into cosmic interconnectedness and humanity's small yet meaningful place within the vast cosmos. These luminous cosmic dancers inspire us to exploring fundamental questions of sometimes poetically named the celestial. This captivating system vividly demonstrates the immense drama unfolding in the universe. Encounter of years ago, a sudden explosive impact, but in a slow, graceful gravitational attraction. These two once-in-spiral galaxies initiated an elaborate geography, reshaping their features and star power. Each tinding into interstellar tells its own story of galactic up. These elongated streams of gas and dust, tens of thousands of light-years, are not merely remnants of but hold potential. Eventually, these will condense into new stars and planetary systems, this dynamic region a spectacular stellar nursery. This galactic factory symbolizes the universe's ultimate recycling, where even destructive forces fuel new creation. For astronomers, this interacting pair provides a remarkable, offering clues about galactic history and destiny. Consider, for instance, the fascinating starburst region about these intertwined galaxies. Stellar nurseries form stars at a rate greater than the Milky Way. These regions allow scientists to study shock waves produced by gas collisions, unlocking secrets of galactic in the early universe. Infrared and radio observations uncover even more hidden features, reservoirs of molecular gas, the foundational ingredient for star formation. Although galactic collisions disrupt of gas, they also compress it in select regions, initiating star formation through powerful cosmic chain reactions. This process produces a brilliant tapestry of new stars, some destined to shine brightly for years, while others end turbulent lives as supernovae. Supernovae occur abundantly in the stellar bridge of galaxies, a region of densely packed stellar populations. These dramatic stellar explosions release massive energy, heating surrounding gas and accelerating cosmic cycles of renewal. Supernovae also produce heavier elements such as iron and gold, dispersing these critical building blocks across space. Eventually, these elements enrich subsequent generations of stars, planets, and potentially life itself. Thus, these colliding galaxies represent not just a cosmic encounter, but a stellar forge, crafting materials for future cosmic ecosystems. One particularly intriguing aspect of this is its insights into galactic cores. Each galaxy possesses a central supermassive black hole encircled by swirling gas and stars. As the galaxies merge, these black holes will eventually unite in a monumental cosmic event, forming an even larger singularity. The ongoing process offers astronomers a unique study black hole dynamics, including mergers that send gravitational waves rippling through itself. Consequently, this spectacular interacting system is more magnificent. It serves as a gateway to revolutionary physics. The galactic mosaic, as some prefer to call these interacting challenges our perception of cosmic time. The merging process, dramatic from our perspective, actually unfolds across hundreds of millions of years. Throughout most of its history, the galaxy's transformation remains invisible to the human eye, yet advanced simulations enable astronomers to reconstruct the timeline of their encounter. By comparing current observations with these simulations, scientists predict the future shape of the resulting elliptical galaxy, which will likely shed the spiral arms characteristic of its original components. Yet this stellar tempest is not only about vast, galactic-scale events. On smaller scales, it provides crucial insights into the behavior of individual star mergers. Many stars' turbulent environment into massive globular feigning millions of stars. These clustered survivors of cosmic upheaval will likely orbit the new galaxy for billions of years. Studying them grants astronomers important clues regarding conditions prevalent during the earliest stages of galaxy formation, as globular clusters often preserve evidence from the universe's infancy. On the outskirts of these interacting galaxies, where tidal tails stretch like ethereal threads into intergalactic space, lies another mystery, the ultimate fate of ejected gas and stars. Some of this material may escape entirely, joining the broader intergalactic medium, while other portions may eventually return to the galaxies themselves. This interplay between creation and loss underscores the transient nature of cosmic structures. Observing this spectacular go resembles watching the opening act of a play spanning billions of years, yet the themes it conveys remain timeless. Chaos and order, destruction and renewal, stellar birth and death, all reflect universal cycles playing out across every scale. These merging cosmic giants remind us of the interconnected nature of existence, like atoms to enormous superclusters. Telescopes reveal the galactic entanglement. We witness more than a mere collision of galaxies. Instead, we glimpse the very mechanisms that have shaped the universe since its inception. In their remarkable complexity, these colliding galaxies embody the universe's boundless creative potential. They form an eternal symphony of motion, light, and transformation, prompting us to ponder humanity's role within the infinite cosmic fabric. Their slow evolution toward a unified structure reminds us that in the vast expanse of space, no object truly exhalation. Every star, galaxy contributes to a grand narrative, shaped by energy and time. The cosmic harmony of chaos, as these interacting galaxies are known, creates a visual nanning countless present. Action sheds light on processes that have defined galaxy evolution since the universe's earliest days. Each tidal tail, starburst region, and star cluster within this cause a chapter of this larger universal story, a story marked by growth, transformational cosmic force. One of the most striking features of vision twins is immense stars and gas outward. These tails, sculpted by gravitas during the galaxy's spiraling approach, resemble threads pulled from a cosmic tapestry. Amid this apparent chaos lies hidden order. Tails serve as highways transport stars to new regions, fostering the formation of future celestial systems. Within these extensive tidal streams roam rogue stars, celestial wanderers ejected from their galactic homes during the collision. Scattered through intergalactic space, these lonely travelers to the galaxy's turbulent past. Astronomers exploring these gravitationally formed streams have also identified disrupted star clusters and protosystems, potential seeds for new astronomical objects, offering valuable clues about the collision's dynamics. At the heart of this merging marvel lie the cores of N38 and NGC 4039, inevitable collision course. This imminent merging of galactic cores holds monumental significance. Each galaxy harbors a supermassive. Whole mergers are not the only dramatic changes unfolding at the center of these interstellar titans. Dense concentrations of gas and dust undergo intense compression, triggering bursts of rapid star formation. This intense activity reshapes galactic cores, fueling feedback young stars and subsequent supernova explosions heat surrounding gas by influencing future star formation. These central regions become a simultaneous creation and destruction. Another captivating aspect of this duo lies in how it alters not just physical structures but chemical composition as well. Vigorous starburst activity triggered by the encounter synthesizes heavy elements, or metronomical terms. These metals, forged within stars and dispersed by supernovae, enrich gas, establishing conditions favorable for planetary formation, potentially even life. In this way, these merging galaxies are actively preparing the stage for future worlds. Beyond visible wavelengths whirling chaos, multi-wavelength observations unveil even more hidden phenomena. Infrared astronomy penetrates dense dust clouds, revealing obscure regions. X-ray observations expose high-energy processes, such as black hole accretion supernova remnants. Combined, these varied perspectives enable astronomers to develop a comprehensive understanding of processes occurring within this remarkable galactic interaction, ranging from microscopic scales to vast cosmic dimensions. Observing this cosmic tapestry also allows us to peer into the distant past. When telescopes capture their light, we observe events as they appeared approximately 60 million years ago, at the speed of light. Thus, these galaxies serve as cosmic time capsules, presenting snapshots of ancients. This temporal dimension deepens their intrigue, emphasizing the immense scales of time and space shaping our universe. The future of these interacting galaxies proves fascinating. As it progresses, individual identities gradually dissolve, and spiral onward, leaving behind a more amorphous elliptic. This future structured by star formation and black hole activity during the merge of these cosmic transformation on scale. Although the complete meta require hundreds of millions of years, it is a reminder of the universe's cycle. In studying these gravities, astronomers' insights into the future of our own galaxy. The Milky Way is destined for a collision with the Andromeda Galaxy in about years. Future seems distant. Observing the cosmic dance between these galaxies helps scientists process colossal. By examining interactions, the full elliptical galaxy stripped of the delicate spiral structures that once defined its predecessor. Ballast curiosity fires all, striking images of their swirling arms and engines of star form iconic representations of the universe's beauty and complexity. They invite contemplation of the vastness of space, provoking reflection on our place within this cosmic expanse. These galaxies represent of creation mirroring the universe itself. Topic observations or scientific analyses, they offer opportunities for discovery and wonder. They serve as a vibrant testament to the universe's limitless creativity, a symphony of gravity, motion that inspires generation after generation. The intricate dance of NGC 4038 and NGC 4039 unfolds slowly, each detail, tidal tails, brilliant star formations, and chaotic collisions, forming an epic tale of cosmic transformation. These galaxies remind us that the universe is an artist, painting with gravity, time, and light. As these celestial dancers gravitational interaction, waves of star formation ripple outward. Massive, short-lived stars ignite quickly, ending in explosions that scatter newly created elements into. These stellar fireworks enrich surrounding gas clouds, fueling future generations of stars in an endless cycle of destruction and rebirth. Amidst this violent environment emerge globulars, surprisingly stable formations of stars. These clusters, forged in turbulence, the collision resultant galaxy as relics of its past. Examining stellar groupings provides clues about conditions present during the earliest phases of galaxy evolution. Much of the drama unfolding in the cosmic ballet of visible wavelengths. Infrared observations reveal hidden information concealed by dust, while X-rays unveil phenomena, such as supermassive black hole supernova remnants. These multi-wavelength scientists to construct comprehensive portraits of galactic evolution, from the smallest structures to the largest processes. The gravitational interplay between NGC 4038 and NGC is gradually drawing their cores, setting the stage for an eventual merger of their supermassive black holes. This monumental event will produce gravitational waves powerful enough to ripple through spacetime, representing one of the universe's momenta and a crucial area of astrophysical research. Yet the dramatic transformations extend beyond their cores. Gas and dust gravitational force in star formation, fuel loops where supernovas reshape their surroundings. This interaction transforms galactic cores into centers of simultaneous creation and destruction, reshaping their environments. Another remarkable outcome of this collision is the enrichment of the interstellar medium. Heavy elements produced during starburst events are scattered throughout the galaxy, creating favorable conditions for planet formation, potentially life itself. Thus, giants are not merely evolving, they are laying the groundwork for future celestial worlds. Beyond the visible spectrum, observations in infrared and radio wavelengths unveil hidden star-forming regions obscured by dense dust, while X-rays reveal high-energy phenomena such as supernova remnants and black hole accretion disks. This rich, multidimensional view offers astronomers deeper understanding of the cosmic forces shaping these celestial structures. When observing these galaxies, we look 60 million years into the past with the finite speed of light, turning our telescopes into cosmic time. This temporal dimension adds depth, immense scales defining our universe. Ultimately, as they continue merging, their original identities will fade. The delicate spiral give way to a featureless elliptical galaxy, home to billions of stars born through past turmoil. Although the transformation unfolds slowly, it underscores the cyclical nature of cosmic evolution, highlighting that even vast cosmic structures are transient and interconnected. The collision between these celestial giants provides astronomers a unique laboratory, offering an unparalleled opportunity to witness the dynamics that shape the cosmos. Each tidal stream, burst, and cluster within narrates part of the universal story, one of growth, transformation, and cosmic forces. In their eternal cosmic performance, these galaxies remind us that, in the vastness of space, is truly alone. Our galaxy, and atom is interconnected, bound together in a universal narrative crafted by gravity, energy, and time. The tidal symphony of these interacting extends beyond their visible boundaries. Long, graceful tidal tails stretch into intergalactic space, forming the merging galaxies with the broader cosmic environment. Filled with stars, gas, and dust, these tails are vibrant zones where material ejected during collision encounters the surrounding interstellar medium. Occasionally, such debris coalesce into entirely new structures, known as tidal dwarf galaxies. These nascent systems represent the universe's remarkability to create amidst chaos. Astronomers studying the gravitational ballet of NGC 40 also gain deeper insights into stellar life cycles. Massive, short-lived stars born in starburst regions emit intense radiation and stellar winds, sculpting the surrounding gas clouds into intricate brightness. These stars end dramatically in explosions, enriching the interstellar environment with heavy elements, building blocks for future stars, planets, and potentially life. This interplay between destruction and creation within the celestial collision underscores a fundamental cosmic balance. Though these galaxies are engaged in violent, they simultaneously sow the seeds for new generations of celestial bodies. Material during their encounter will eventually cool, fresh stars and planetary situating the universe of renewal. The merging 4038 and N39 into a unified elliptical galaxy will mark the culmination of this extraordinary transformation. Stringent spiral arms, the new galaxy meant to housing a supermassive black from the fusion of its predecessors' cores. Fused with elements produced throughout their interaction, this new celestial structure stands as a testament to gravity's power as galaxies continually in this eternal embrace, exploring profound cosmos through these interacting giants. They serve as windows into galactic evolution, both past and future, insights into our own galaxy's eventual encounter with Andromeda billions of years from now. Powered by human curiosity and advanced technology like the Hubble Space Telescope, ALMA, and the James Webb Space Telescope, researchers have uncovered unprecedented details of these merging galaxies. Each new discovery adds layers of understanding about cosmic dynamics, enriching our appreciation for the complexity and beauty of the universe. These galaxies, often poetically described as the luminous chaos, are all worldwide. Striking images of their swirling arms and brilliance remind us of the vast majesty of space, prompting questions about humanity's place in its narrative. They challenge us on our own to seek answers to profound existential questions. The infinite tapestry of cosmic entities continues to unravel gravitational, temporal, and energetic. They are living universal processes, every tidal stream, starburst, ocular cloud offering clues to the fundamental mechanics of cosmic evolution. In this galactic cascade, complexity reigns. The gravitational between these galaxies fling material into luminous arcs spanning of light years. Far from mere, these tidal streams seeds for new celestial systems and galaxies. Within them galaxies, miniatures providing value to how the universe's earliest structures may have formed. Part of the light forms with extraordinary intent. In molecular gas, compressed gravitational inert stars exceeding thick activity. These dynamic regions brilliantly magnet offering astronomy a processor and the dynamic force galaxies. Thus, interaction on symbol and renewal, continually reshaping our understanding of the universe. Within these stars, the most massive stars burn brightly but briefly, ending their short lives in dramatic supernova explosions after only a few million years. These supernovae are spectacular cosmic displays. They play crucial roles in galactic evolution. They release enormous energy nearby gas and propelling powerful stellar winds outward. Winds reshape the forms and cavities that can either of star formation the process entirely. Cycle of cosmic feedback. The nature of this extraordinary. Yet supernovae accomplish more than merely surrounding. They also enrich it. Heavy elements like carbon, oxygen, created within the cores of massive stars, are dispersed by these explosions throughout the surrounding. These elements serve as critical ingredients for fusion and possibly life itself. In this way, these stellar laboratories function as cosmic alchemists, seeding the universe with necessary for future worlds, continuing a process ongoing since the earliest epoch. The hidden realms within these celestial giants are equally intriguing. Infrared and radio observations reveal vast cold molecular gas, key fuel for star formation, concealed within the chaotic regions of these galaxies. Optical telescopes, this gas is fundamental to their evolutionary future. As gravitational forces compress and heal potential raw stellar populations, ensuring these cosmic entities will shine brilliantly for millions of years. Simultaneously, X-ray telescopes have uncovered intense activity within the cores of detecting power from accretion disks surrounding supermassive. galactically consume vast amounts of matter, radiating materials. Passive observers, these black holes shape their host galaxies' powerful gravitational fields, influencing star formation on galaxies. As this interstellar duo moves slowly toward an inevitable merger, gravitational interactions will intensify dramatically. Over hundreds of years, these galaxies will increasingly becoming ever more distorted and lose identities. The delicate spiral arms that distinguish them will disappear, replaced by a chaotic and amorphous structure. In the merger's final act, their central supermassive black holes will collide, emitting powerful gravitational waves rippling through spacetime itself. This ultimate merging will give birth to a new elliptical galaxy, combining the stars, gas, and massive black hole remnants of both predecessors. The resulting galaxy, smoother and more spherical, will stand as a testament to cosmic transformation, enriched by elements created during its formation. It will provide fertile ground for continued stellar and planetary, echoing the ongoing cycles of cosmic renewal. For humanity, this celestial event is more than a distant, it symbolizes cosmic inspiration. It reminds us of the universe's vast scale, the immense forces that shape it, and the beauty that emerges from these powerful processes. These galaxies invite contemplative dramas unfolding across the universe, each as dynamic and intricate as the dance we observe here. Through their gravitational cosmic titans mirror universal cycles of life, death, and renewal, demonstrating that destruction often serves as a creativity. They teach us to embrace change, find beauty amid chaos, marvel at the infinite possibilities inherent in the cosmos. As astronomers continue this tidal symphony, every new observation deepens our understanding of galactic evolution and the universe itself. Each discovery adds layers of complexity, further revealing the boundless creativity of the cosmos. These galaxies serve as cosmic masterpieces, inspiring awe and curiosity, and inviting us on an endless journey of discovery across space and time. This endless cosmic saga, as these galaxies are often described, continues to unfold on timescales beyond human comprehension. In their gravitational embrace, they offer a vivid example of forming chaos into order, destruction into creation, turmoil into harmony. This grand narrative, expressed through gravity and starlight, resonates profoundly across the cosmos. The galaxy's title among their most dramatic features. Streams of stars, gas, and dust reach like cosmic bridges into intergalactic space. Within these immense arcs, isolated stars journey as cosmic wanderers, carrying ancient light across the darkness, bearing witness to their traditions. Moreover, the tidal arms host intricate knots of gas and dust, where star formation actively begins. These regions, compressed by gravitational forces, serve as stellar nurseries, the next generation of celestial bodies. By studying these nurseries, astronomers gain insight into star formation's earliest moment and conditions essential for the birth of stars and planets. These tidal streams thus represent more than mere relics of galactic disruption, they are vibrant zones of cosmic rebirth. At the heart of this galactic fusion ballet, the galaxy's super-black holes are spiraling toward an eventual merge, the immense bursts of gravitational waves, ripples in spacetime detectable across vast cosmos. These waves will carry echoes of the galaxy's violent dance far into the universe, allowing astronomers to study study in detail the dynamics of such monumental interactions. Yet, even now, long before the Black Light, the cores of these celestial entities are astonishing. Regions, known as active galactic nuclei, brilliantly powered by intense radiation emitted from hot accretion disks. As gas well black enormous amounts of outward galaxies chaotic transformations from within. Simultaneously, tempest rages attracting galaxies, fueled by the mission collision of molecular gas. Powerful waves of star formation ripple through their structures, igniting millions of new stars that blow across the cosmos. These newly born stars and short-lived surroundings with intense ultraviolet radiation and stellar winds. Their rapid deaths in supernova explode heavy element iron space experimentary systems. Creation within the forge exemplifies cyclical galaxies appear locked in a violent dance, their vital role in cosmic. Without such tumultuous events, the universe would lack the ingredients necessary for its oceans, molecules, and ultimately life itself. As the turge, their spiral forms dissolve into more chaotic and amorphous shapes. Eventually, the elegant spirals will disappear, leaving behind a smoother elliptical galaxy. This new entity will embody the legacy of its predecessors, home to countless stars and enriched with materials forged through the turbulence of their. At its center will lie a unified, massive black hole, the remnant of their dramatic collision and a testament to power. A galaxy born from NGC 4038 and NGC 4039 will itself evolve, possibly encountering other galaxies over billions of years, continuing the cycle of mergers and interactions that characterize the cosmic web. With each new collision, it will grow and change, continually shaping its legacy across cosmic timescale. For us, these celestial titans offer infinite avenues of discovery. Every uncovers fresh details, from the intricacies of tidal tales to the mechanisms of star formation and black hole interactions. Advanced instruments like the James Webb Space Telescope deeper insights, opening new complex entry. Yet these galaxies serve humanity beyond scientific curiosity, awe and contemplation. Their breathtaking, vivid and dynamic vastness of the cosmos, the incredible forces at play, and our own place within its grand narrative. Their cosmic collision mirrors universal themes of transformation. They demonstrate vividly that destruction is not an end but something new. Galaxies invite us to embrace change, to recognize chaos, and the universe's endless potential for creativity. It continues into this ongoing tidal symphony. Each discovery enriches our of cosmic evolution and fuels our collection. These galaxies represent a living masterpiece of cosmic creativity, sparking wonder and curiosity among all who gaze upon them. Still unfolding, inviting humanity on a timeless journey and imagination. The endless saga of NB30 4039 continues to evolve on scales beyond human comprehension. Gravitational embrace symbolizes the universe's extraordinary ability to shape chaos into order and into creation and to harmony. Told through gravity and starlight, their narrative echoes, offering humanity a window into profound cosmic forces. Among their most captivating features are the galaxy's tidal tails, ethereal, luminous bridges extending into the intergalactic void. Within dreams, isolated stars wander as cosmic nomads, expelled from their original homes by gravitational upheaval. Despite their isolation, these stars carry ancient starlight of their origins, journeying endlessly through space. Embedded within these expansive tidal arms lie intricate knots of gas and dust, stellar nurseries actively forming new. These regions, computational disruptions, provide fertile grounds for future celestial bodies. Studying these nurseries grants astronomers insights into formation's earliest, illuminating conditions necessary for star and planet formation. Far from mere remnants of collision, these tidal structures signify vibrant rebirth and renewal within the cosmos. At the heart of this galactic fusion ballet, the interaction between the cores of NGC 4038 and NGC 4039 vividly demonstrates gravity's immense power on a cosmic scale. Each galaxy's center, anchored by a supermassive black hole, is gradually spiraling inward due to their mutual gravitational pull. The future collision of these unleash a dramatic surge of gravity waves, ripples in spacetime traveling across vast cosmic distances, detectable by advanced observational instruments, carrying echoes of this spectacular galactic merger. Yet, even now, far before that ultimate black hole merger, the activity around the galaxy's cores remains captivating. Surround black hole accretion disk and dust spiral, heated to extreme temperatures and radiating energy across the electromagnetic spectrum. These active galactic AGN shine brilliantly, illuminating and mark as the most energetic of these celestials. The star triggered by this merger is another vital chapter in their cosmic narrative. Waves of intense star formation ripple throughout the combined galactic structures, giving rise to vast populations of massive, short-lived stars emit intense ultraviolet and powerful stellar reshaping interstellar intricate bubbles and filaments. When these mass novae, they scatter heavy elements, carbon, oxygen, iron, across the interstellar medium stage for the formation of a planetary system. The dynamic interplay between creation and destruction in this cosmic forge symbolizes the cyclical nature of universal evolution. Though collision is enriching the cosmos necessary for each interaction as it would thus conditional dance, distinctive spiral structure increasingly disrupted, more amorphous, elliptic. This cyclical galaxy, smoother, will embody the legacy of its predecessors. Enriched by elements produced during the collision and its supermassive at its core as a permanent transformational power of gravity. Over billions, this newly formed elliptical galaxy to evolve, but with neighboring galaxies, perpetuating cycles of galactic evolution. Each subsequent merger contributes mass, complexity, legacy, into broader story of the universe. For astronomers, this gravitational ballet avenues of and discovery. Each observation complexity interactions to mechanisms and blacks. Edge instruments, such as space telescopes even more detailed, provided insight. These transformative scientific value embody profound cosmic dynamism and intricate human imagination on the universe's vastness. They consider our place within an infinitely large, exploring questions about existence itself. In their collision, these celestial type the universal cycles that govern all. They illustrate is not an end but of transformation, enabling renewal and growth. They inspire potential within chaos, recognizing the endless possibility by the cosmos. Research progresses, each discovery deepens our understanding as work revealing its boundless creativity. These merging galaxies' masterpieces, stimulate and curiosity, encouraging us into cosmic mysteries. The ongoing NGC 4038 and 4039 cosmic ballet continues to captivate astronomers alike. Gravitation illustrates the universe chaos into harmony, turmoil into creation. Expressed through starlight and gravitational forces, this grand cosmic narrative resonates profoundly, offering human insights into the immense force in our universe. Their distinctive tidal tails, spectacles of stars stretch outward into Inter-Galactic luminous threads. Within these streaked stars wander travelers, carrying memories of their violent origin. Yet these tales are sites of renewal, clusters of gas and dust and new stars, proof of the universe's remnants and active power. Thus, this galactic collision is a testament to cosmic evolution, thus that even amid chaos, the universe continues to renew, weaving order from disorder and destruction. Even as the time approached these within them continue scientific insights. Indications have uncovered of star formation by dense dust cloud optical telescopes enabled by observatories like the James Telescope. Astronomers use of the galaxy's most active and dynamic, revealing the intricate mechanism of transformation. Simultaneously, telescopes map the cold molecular gas, the flux of new stars, illustrate vital resource and consumed collisions. The galactic occurring within these seas provides an opportunity to study Phoebe's crucial evolution. The combustion released by young supernova explosions, and actively shapes their structure and behavior. In some regions, this compresses gas, ignites of star formation, while else material entirely, suppressing future. Standing this delicate balance for deciphering galactic throughout the universe. The product of this profound cosmic symphony of destruction and creation will be a galaxy, markedly different structures of NGC-4 and NGC-9. Optical galaxy, will be enriched and synthesized during the setting the nation of new systems and potentially life-bearing worlds. For humanity, the eternal dance of these galaxies telling scientific endeavor reminder of our cosmic dynamic and breathtaking encourage us to ponder the universe forces shape humanity's place with narrative. As their saga unfolds, these galaxies remind us of connectedness. Processes at play here mirrored countless other galaxy way. They highlight a shared history, written in stars and gravity, verse as a ever-evolving, where even violent rise to new order and beauty. In this context, the galactic Renaissance 4038-4039 transcends symboliance, an endless cosmic inspiring explore, imagine the infinite possibilities. Their narrative is continuously inviting new cosmic wonders and embrace the myth our current understanding. Orchestration energy is an enduring narrative of complexity. The Inter serve as cosmic laboratory playing dramatic fundamental to galaxy and evolution. Their destruction and renewal hundreds of years found insights into uses at work across space and as giants closer, their spires are gradually disrupted and to immense tidal sending far into intergalactic. Within these loopholes, stars and dense gas into new stellar demonstrating cosmic collisions reproduce debris. These also give rise to dwarf galaxy miniature, independent star systems forms collision debris. These dwarf galaxies provide astronomers with insights into rapid galaxy formation processes, resembling conditions in the early universe, when galactic mergers were far more common. The heart of these merging galaxies, powerful gravities compress gas and dust of star-forming regions. Acceleration ignite of short-lived stars that surroundings with intense radiation. Event stars end their brief lives in dramatic explosions, surrounding gas with essential heavy elements like carbon and iron, ingredients formation and life. Thus, even this extraordinary collision illustrating that define a necessary creation. These interacting galaxies the universe's endless transformation, recognize beauty and possibility upheaval. Visible symphony wavelengths beyond human sight reveal deeper insights into the forces shaping these colliding. Infrared unveiled dense clouds concealed within the and galactic core. Shrouded by Earth's visible wavelengths, ocular gas serves as raw material for star formation. Mapping its flow enables astronomers to build pathways, uncovering how new stars and cosmic X-ray observations of energy phenomena unfolding in GC 4038-4030. These energetic emissions arise from hot, diffuse supernova explosions, as well as from luminous disks orbiting black holes at each galaxy's heart. These massive, millions of times more massive than gradually spiral inward toward each other as. Their event will unleash powerful gravities, ripples in spacetime that provide opportunity to study the extreme physics of black holes. The event these gravitations clear to form a single, cohesive galaxy. This newly formed elliptical galaxy, lacking the arms 1 GC 4030 AC 4030 nonetheless stand luminous. Richly infused with heavy-aided throughout the collision, an ankle, unified supermassive black it will serve as a monumental gravitational cosmic resilience. Yet, the Saw Giants does not conclude with their merger. Will continue eventually encountering these fresh rounds of cosmic interactions. New encounter will enrich its complexity and reinforcing galaxies are never static. A dance and inspiration, making beauty remarkable and to explore in seek antennae distant galaxies more than distal phenomena realize the universe's capacity for creative formation and renewal. Their story embodies the eternal govern existence of the interconnected chaos and destruction, and studying their evolution deepens our understanding and highlights the beauty and universal transformations. The finale of NG38 and NGC 4039, as they climax perform not merely a profound one whose impact will reverberate across cosmic timescale. This encapsulates the very universal evolution, vividly how destructive opportunities for order. This pivotal galaxies offer an about the infinite cycle of death, and rips the cosmos itself. In the coming hundreds of years, these two galaxies will be intertwined. Distincts, all and stretcent dissolve into an intricate mass, gas, and cosmic dust. The elegant structures that each galaxy will transition into a more amorphous shape as their unique gradually fade. Yet, hidden within this apparent chaos is a deeper purpose. It's not merely the destruction of two galaxies, it is something entirely new. Central to this cosmos will be the eventual merger of their supermassive black hole. These enormous gravitons, millions of times sun, slowly toward each other. As their paths inevitably, they will gravitational waves propagating through spacetime itself. This black hole merger, one of the most eminent in the universe, will be detectable by gravitational wave observatories in the distant future. Ultimate climax transformative dance. The resulting, likely elliptical in shape, possess luminosity. It will lack spiral arms that rise its, yet it will remain undeniable. Instead, its stars will spherical halo, gravitational force it. This ellipse will combine and carry forward the heavy elements in its tumultuous formation, such as carbon, oxygen, and essential ingredients for future stars, planets, and life itself. Format will prove its turbulent past globular clusters, dense of stars created collision star form. Each cluster, harboring millions of, will orbit the elliptical enduring relics of its gens. Within these clusters and their planetary systems may one day be by extending the galaxy's legacy in ways imagined. Elliptical galaxy's new cosmic form, it will continue to evolve of years, interacting galaxies cycle of Einstein's galactic. Future encounter will complexity, stars, gas, and dark matter, ensure continues indefinitely. Cosmic legacy galaxies extend their physical structure. By studying them, astronomers gain insights into universal how gravitational force galaxy structure, how interstellar space, and black hole environments. These galaxies shall benchmark galaxy offering of cosmic beatific importance celestial entity to envision scales beyond orients. Their complex evolving structures, and captivating us to reflect upon the vastness and our interconnectedness with all cosmos, remind us of the human discovery, beyond our very home endless cosmos. As it travels millions of years across the reach our telescope celestial the profit between time and the universe, helps us to the distant past, a connection between times, and our understanding of cosmic evolution. These merging timeless message of resilience, and destruction of this creation, embodying the universal ability and complexity. These cosmic interactions remind us that nothing, stars, and even entires can reshaped by forces, star formation, and powerful. Thus millions of years powerful humanities played their cosmic. Just as reshaped by gravitation, so too is our existence the same universal process of celestial bodies. The elements that make up in the horn and disperse like these dramatic galactic mergers. The final chapter of these companions is not merely an ending, it signifies the start of an era. Luminous aftermath, a galaxy will emerge, embodied from the cosmic entity. This future will carry the enriched generators, providing fertile ground for future planetary systems, possibly life. As we gaze upon it, we glimpse and future, a future continued by the additional forces processes unfolding. These galaxies stand as living cosmic potential, that even within chaos, the universe renewing tapestry of endless, inspiring humanity to imagine and marvel of existence. That is optical phenomena, most notably nebula, NGC 3. This planetary nebula, approximately 650 Earth in the constellation Aquarius, has captivated astronomers due to its strike to a human eye. And its visual a helix object investigation in cycle of dynamics of interstellar. This nebula final stages of a sun-like star's evolution. When a star exhales fuel, it red jets, cloud of ionized gas. The central remnant emits ultraviolet, causing material. The result display of gas, rich in oxygen and nitrogen. The structure of the nebula, stellar winds and radar, reveals interplay between environment. Observations called cosmic eye have been instrumental in advancing our understanding of imaging. Like the spectroscope has allowed us to analyze the composite, detect oxides, essential for planetary. Meanwhile, space resolution images have provided a detailed view of its intricate filament gas, remnants of the stars interacting with the interstellar. The celestial is a laboratory transition stars back into the cosmos. It disperses over thousands of elements it contains will eventually contribute to the stars and potential bearing world. This of stellar materials the interconnected evolution. Beyond the helix other nebulae residual pupil universe, each offering unique to astrophysics. The 6543 constellation Drake example displays a highly within a turbulent biosystem. These observations planetary nebulae, despite are far more astronomed. From a broader perspective, study of the universal ocular structures is vital for the fate of our own sun. Approximately 5 billion, our star will undergo transformation for layers and leaving behind dwarf. By analyzing nebulae, astronomers how this process, offering a distant future system. Furthermore, the galaxy extends beyond optical astronomy. Radio and X-ray telescopes have detected planetary nebulae, energetic interactional remnants and their environments. These multi-wavelength scientists are the puzzle solution processes that set both microscopic and cosmic. With the heavenly limited to astronomers, these formations has been striking imagery, often for science publications and releases. The Helix Nebula, in particular, has been dubbed the Eye of God in cultural and artistic symbolizing the vastness and mystery of the cosmos. As technology advances, new observational methods test the depths of these stellar. Upcoming space missions, James Webb Space Telescope uncovers of nebular structures, physics of dying stars and their cycle. By continuing to celestial formations, we our understanding of astrophysics but also reinforce connection to the universe. Material vision, as seen in nebulae resembling as represents the aesthetic universe, it is profound astrophysics. As observational techniques astronomers continue complexities hidden cosmic shedding light on the processes governing interstellar chemistry, and the between destruction in the universe. The most intriguing aspect gaze is the chemical enrichment of the cosmos. Stars clear forges, synthesis through fusion reactions or billions of years. However, the treatment of these elements occurs during the final stage life. The helix, like other similar, is rich in heavy carbon, oxygen, materials that are incorporated into new generations of planetary system. Without this, the fundamentals of life, ocean nebulae serve as crucial links in the cosmos. Recent using spectroscopic analysis deeper insight into the celestial observer. By anode light at different wavelengths with the cyclic aeromans, organic form in the planetary nests that contribute inventory of the interstellar. This discovery has significant astrobiology indicates that life is a universe by dying star. B contributions make Sentinel offer a glimpse of stellar radiation-driven. The shaping of planetary influenced by multiple factors including the stellar wind star, and even potential with companion stars. High-resolution imagery has revealed asymmetric structures at many of these gravitational interaction forces. Observations of the Galactic Observatory telescopes presence of collimated outflows, high-velocity streams of ink from the central source, appearing as polar lobes, evidence that the central may have undergone compensing the final. Such challenge early depicted plainly as simple, and instead more chaotic. Furthermore, comical light plays a role in the broader galactic. The material ejected from does not simply dissipate, instead, it enriches surrounding molecular cloud where new stars are born. This continuous recycling of stellar material that each generation of star heavier elements than the previous one, gradually equal composition of galaxies over cosmic times. The structure for a major leap forward of telescope Webb space JWST unprecedented capability expected to provide an even clearer view lens, allowing peer deeper to region by thermal emissions, distribution of nebular material, further refining our understanding of stellar evolution. Beyond space, advances in astrophysics have allowed simulate the formation and celestial portal. Incorporating radiation transmagnetic fields, are provided for how planetary nebulae develop. Some of the suggest intricate nebulae such as filaments, arcs, and knots, are the result of interstellar winds alone. These processes not only for nebular studies but also models universal atoms beyond astronomy. Throughout history, symbols of an eye-like structure in space has such association. About cosmic symphony viewed for the universe itself. Such interpretations lie out scientific inquiry the profound impact on human thought. As we continue to observational tools and theoretical heavenly sentinel remains of discovery. With each new data astronomers are pieces of rebirth in the vast cosmic web they help to shape. The more we study these celestial, the clearer it becomes that the universe is not a static ending, evolving system or even the REM stars controls. Thus, just a speckled treasure trove of secrets push human knowledge. Whether through advanced theoreticals, each new understanding the mechanism the cosmos place within it. Cosmic embodied in nebulae such as the helix to intricate dance, demise, each shape formation bites into the dispersion of elements, and nature of the telling aspects of the aperture and tracing kinetic gas expelled from observable wavelengths from X-rays, have revealed that the temperatures within these nebulae can vary dramatically. The outer, composed of cooler gas, glow primarily in infrared and optical, while the inner, heated by the remnant, emits in the X-ray spectrum. This product of focusing the surrounding material and gradually to space. High-resolution spectroscopy have uncovered that the stellar distinct velocity sujection of material uniform but in pulses or outflows likely resolutions in the dying star causing it to expel at different rates over thousands of years. Studying these expansion rates can planetary nebulae, offering a formation to patient. The galactic also central to station. As stars share also solid particles, silicates, carbonaceous grains, and even tears. These, once released can act as planetary of nebula celeste shown that these can survive periodically new stars. Understanding how these evolve is crucial for origins of terrains using radio details of universal level. Magnetics play a role of planetary nebulae. Some of the multiples of these seen with lobes particle long leading out structure shells. Of such magnetics that die possess previously magnetic activity. Another layer of our understanding of ethereal gate clearly a relic of stellar death entity, continuously evolves into interstellar. Observations planets burst with their surroundings, shock waves from these nebulae cavity can potentially of new stars. Star formations the interconnected nature of cosmos, or even it's to the Looking toward next-generation astronomical instruments will further understanding of the spectral sentinel. Ground-based observatory adaptive optics are all sharper details, obviously unseen in the Space-based James Scope, astronomers tour into the of planetary uncovering physical conditions clouds. More of the heavenly heavens be nebulae to pattern. Comparing nebulae galaxies valuable the chemical the elements in distant astronomical galaxies enrich themselves, revealing the gradual build-up and ascent formation. Ultimately, following exploration of the sentinel reinforce Earth, the universe being interconnected where every phase contributes to the greater goal. Dust and by dying vanish into oblivion become part of structures, planets, stars, or the stellar medium that sees. The continued systematic formations is not just a glitch but also a reflection deep-rooted curiosity about the cosmos. As in these celestial eyes out the universe, minded that ours is intricately stars and once for ancients. Thus so gave the science and the cosmic reminder itself is evolving the few comprehend. Sentinel, as seen in nations of planet, continues to sow into the cosmic process of transformation. Each adds new understanding of how the stellar medium the next celestial. One of the most cosmic role of binaries in shaping Earth. Early modern nebulae assumed the spherical expansion of gas and high-res has demonstrated these formations that can highly bipolar outflows, spiral path, intricate filament presence of the gravitational nebula. These lead to mass angular momentum redistribution of dense equatorial lobes of gas. Recent research using data from the Atacama Large Array has provided detail on the motion of these nebulae. Scientists have developed simple molecule monoxide compound in laboratories. Are crucial for understanding the origin of molecules in space. Nebulae may act as dispersal points for the ingredients of life. The universal also beacons of cosmos, measuring the expansion. Astronomer how long nebula can predict the fade medium, provides a estimating different broader unknown stars transition from to white dwarfs. Additionally, actions of the spavage entering at the cores of nebulae. The remnant white center of these formations often emit strong and X-ray radiation interacts with the surrounding to produce an ionized processes distribution of elements within the nebula, axis or enriching the material not a transformation that can even affection of the gas within the nebula eventually thousands of years will disperse, leaving behind or stellar primarily and however Iris does not itself. The molecules release stars directly to the formeller systems. Regenerating much as the Orion arm of the Milky contains stellar dust and gas, giving them prime citation. Planetary neb catalysts for the next generation evolution. The cycle of stellar continues indefinitely. Future missions, such as the Large Telescope and the Next Generation Observatory, provide even deeper in structure of the astronomical. By spectrograph optics, astronomers will be able to visual knots of gas, trace their and furthers of how nebulae different conditions. Continued the stellar observer stems from fixed significant grand, visually striking phenomena in space. The helix nebula counterparts serve as reminders of the process of the universe. They are not merely star participant narrative, bridge future of stellar in the grand source will get to these of all causes. Reactions with dispersal of galaxies encapsulate matter cycles, influencing formation of planets to the pits of life. As our capabilities expand, theoretical models improve, Guardian will continue point of astronomical with each move one step landing not of stars, but the ripples that govern of the universe itself. The astral sentinel, embodying nebulae, represent these in the stellar evolution. These enigmatic formation cover new layers of complexity that the end of a star's life is an endpoint but a transform that fuels the universe dynamism. Intriguing aspects of Ian is its connection to white dwarf formation. Central star of Nebula has nuclear fusion into a hot core that will arise as a white dwarf. These remnants, those typically no larger, contain the majority of the originals, making them incredible. Over billions of years, they will cool, and their existence provides a glimpse. Our own Sunday studying these objects allows to predict how similar stars, in the distant, the galactic, the interstellar, the expelled stars contain carbon and nitrogen ingredients for pollution. Planetary nebulae, these enriched future stars and plant necessary heavy elements to form rocky worlds, atmospheres, life. Since the planet Earth owes its contributions of that came before, recent advancement millimeter wave astronomy new insights into the molecular occurring within Guardian. Observations using a telescope have revealed the pressure outflows that extend the visible boundaries of these. These outflows, composed of complex and dust Sagittarius nebulae, are dispersing space but actively contributing to the chemical evolution of galaxies. Another critical distinction, the spectral watcher of high ionization nebulae. These ions occur when the intense radiation from the central white collides with the surrounding gas, sharp bound ionized and these appear as knots, like tail from the central. The discovery details just form expansion of nebulae, indicating that instabilities and turbulence shaping these formation. In some, the heavenly found to exhibit vast violent interactions, unseen planetary nebulae, such as the display ring-like, suggest they were a star. A dying star has a close it can lead to complex masses or spiral from a nebular shell. The presence of these structured planetary nebulae tracers for binary, helping astronomy influence of in stages of telescopes to deeper universal sense. The Nancy Space Telescope to launch in the coming will provide wide nebula, allowing catalog planetary nebulae regions of the. Meanwhile, advanced wave astronomy may one day allow us to detect this interactionary nebulae, new window into their scientific value. The ethereal Guardian formation inspire philosophical interpretation. To celestial civilization for eye of cosmic watch gateway to these nebulae serve as universe's value. They illustrate nature of existence, where each star contributes of new world. Ultimately, the astronomy reinforces one of the fundamental physics: the universe is in a constant state of. Stars are not bodies but cosmic net. Births, lives, and deaths influence galaxies. Planetary nebula we observe is on a snapshot of returning to the ready to be. As he continues to push the boundaries of space and cosmic understanding, the celestial is both a tragic reminder of our place. Each is closer to mental existence come from. What will become of our sun? And how do the dying stars shape the fabric of? With every new observation, spectral guardian can reveal its secrets into the mysteries. Danger of planetary nebulas as a celestial archive, a testament to the universe across. As these drift through the vastness of offerings into the past for the fate of future incline. One of the most aspects of the its role in the feats that shape galactic structure, while often considered of stellar death, play actively controlling evolution galaxies. The gas and dust enrich the interstellar, seeding future generations with heavy elements. This process, known as movement, is crucial for rocky planets, complex organic, and even the conditions of life. The study of the astronomical revealed that the dynamics are far more intensely thought. Models depicted planetary nebulae, spherical shell banding uniformly. However, modern imaging has uncovered a surprising diverse structuring from symmetrical allele complex nations. Some elongated lobes feature intricate helicals suggesting that influence their morphology. One of these variations in the is the presence of systems. When a dying star's contractions alter, in some cases secondary star material from the prime dense or spirals of gas that persist initial ejection event. Observations such as the Southern Crab Red Rectangle Nebula have provided evidence that many planetary their distinctive appearances or actions. Complexity, the galaxy also plays a astrophysical chemistry. Infrared spectra revealed the presence of organic molecules in nebulae, including polycyclohydrocarbons, and full carbon-based like spheres or molecules associated with the building, suggest that nebulae serve as laboratories where the raw materials for planetary and evolution are forged. Their presence reinforces organic chemistry throughout the galaxy, fundamental component of planetary the celestial and ideal laboratory physics of winds. The interactantral white radiation and gas creates ions that propagate, sculpting them over time. These are responsible for the point edges and pattern many planetary. By interaction, gain insight into how shape not only planetary also the larger interstellar. Recent computational have allowed researchers to simulate the evolution sentinel with in dynamic pressure magnetic fields to predict nebulae different conditions. Results of these simulations have been consistent with real-world planetary nebulae by complete forces expansion alone. Future of research for dramatic advanced generation of space space telescope and the large ELT astronomers insights into the fine structure composition of these nebulae. With their enhanced these telescopes lists to probe nebulae at higher resolutions, flow of matter on scale unattainable. Moreover, the study of null has profound for understanding our own sun. In a 5 billion year star will enter the red giant phase before forming its own planetary. By analyzing it, astronomers can predict our solar system during this Earth it survived the sun's expansion, the least in the process to the birth of new stars and planetary where in the galaxy, continuous cycle of cosmic evolution. Beyond the realm of astrophysics, the ethereal observer has captured the imagination of philosophers and spiritual thinkers. Its strike to an eye has led many to interpret it as a symbol of a window through which serves itself as the eye of God to the unknown, or a reminder of our vastness of space, serve as powerful metaphor of all things. As our understanding of the eye deepens, so too does for the intricate and dynamic processes that shape. These merely remnants of they are active and story of creation, in element stars journey across the universe. Each new discovery, the spectral germs of fundamental truth, the ever-evolving web shapes the future. In our bodies were weighing stars, the material sun galaxy worlds. This way, planetary remind us that universe is ever only transformed. Guardian, manifested in the grandeur of nebulae, stands as a shield bridging the life stars in an these glow scattered across galaxies more than mere artifact demise, they are agents of shaping the universe in wind far beyond span. One of the most questions about the ether is its role in the ecosystem. The gas and dust expelled by these nebulae disperse and actively participate in the cosmic process. With the interstellar, these elements to the birth of forming clouds that serve as stellar nerves. This exchange of materials the intercosmic phenomena star, nebula, or galaxy isolation, but rather as self-perpetuating system. Recent advances in spectroscopy have allowed probe deeper into the condition of the galaxy, revealing an abundant potential for planetary and biological formation. Observations using the Hubble and James telescopes have confirmed that planetary nebulae are rich in carbon, elements integral to solid planetary bodies and atmospheres. Process unders truth. Without elements by dying, the conditions necessary as we know it could never arise. Structural complexity of the heavenly has also been a subject of while early depictary nebulae spherical expansion, high-resolution imaging has shown, revealing symmetrical patterns sculpted by some nebula-like outflow display strikingly symmetrical and still others, filamentary networks. These devices have led astronomers to underlying mechanisms response variation. One prevailing theory that magnetic fields play a crucial role in shaping the while sun are not typical with strong activity in their late stages of planetary atmospheric influence. The interstellar winds fields could explain the permeated jets and in many nebulae. Confining would reach stage evolution magnetic forces stronger than previously believed. Another infology portal is the present companion. Observations have plant contains sent in cleanse affecting the distributed. In some cases interact in spikes, where the influence to the ejected gas into a thinly spaced ring. Such discoveries suggest nebulae key indicator evolution, offering into the complex gravitational between stars. Beyond stellar media astronomical sentinel its vital ultimate fate of sun. By studying the energy output and white dwarfs left behind these nebulae, astronomers can refine model long-term evolution of stellar remnant. White dwarfs are dense cores of former giant billions of radiant heat until they dark black dwarf exist in the universe. The timescale of formation exceeds the current play offer this distant future. The celestial is not merely a subject of scientific but also a source of philosophical reflection. Striking resemblance to all-seeing widespread collisions, the idea that the universe watching and shaping mythology traditions, the eye symbol of action, like the heel reminds us of the vast embedded in the workings of therein lies and interact with. Do planets influence the formation of arms in galaxies? Could the shock waves from their expanding shells trigger supernovae in neighboring stars? As observational technology advances, astronomers are beginning to explore these larger-scale connections, piecing together the intricate web that binds stars, nebulae, and galaxies into a cohesive cosmic tapestry. With the deployment of more sophisticated instruments, such as the Extremely Large Telescope (ELT), and next-generation space observatories, our ability to observe and analyze the astronomical gatekeeper will reach unprecedented levels. These advances will enable researchers to detect fainter nebulae, track their evolution over time, and even identify planetary nebulae in distant galaxies, providing a broader perspective on their role in the universe's chemical and structural evolution. Ultimately, the study of the spectral watcher is more than an exploration of dying stars, it is a journey into the very fabric of cosmic creation. Every planetary nebula we observe today is a brief but brilliant chapter in a much larger story, a moment in time where a single star's legacy is written in light, gas, and dust. These nebulae are not mere relics of the past but active participants in shaping the future of galaxies, ensuring that the elements forged in stellar furnaces continue their journey across time and space. As humanity's knowledge of the galactic observer deepens, so too does our understanding of our own origins. The atoms in our bodies were once part of a dying star, just as future generations will be formed from the remnants of the Sun. In this way, planetary nebulae remind us that nothing in the universe is truly lost, only transformed, reborn into new stars, new worlds, and perhaps even new forms of life. Thus, the ethereal sentinel stands as both a cosmic masterpiece and a fundamental pillar of astrophysical inquiry. In its luminous beauty, we find the echoes of ancient stars, in its dynamic transformation, we glimpse the endless cycle of creation, and in its fleeting existence, we are reminded that the universe itself is a living, evolving entity, one in which every ending is, in truth, a new beginning. The celestial guardian, embodied in planetary nebulae, stands as an enduring testament to the impermanence and renewal of the cosmos. These breathtaking formations, fleeting in astronomical timescales yet integral to the cycle of stellar evolution, continue to shape the interstellar medium, leaving behind a legacy that extends far beyond the stars that birthed them. One of the most captivating aspects of the cosmic sentinel is its contribution to galactic evolution. As stars expel their outer layers, they inject vast amounts of enriched material into space, gradually altering the composition of their host galaxies. This ongoing chemical evolution ensures that each successive generation of stars forms from a medium increasingly abundant in heavier elements. Without the dispersal of carbon, oxygen, and nitrogen through planetary nebulae, the formation of rocky planets, complex chemistry, and potentially life itself would be far less common in the universe. Observations of the ethereal watcher have revealed its intricate interactions with surrounding interstellar clouds. As the expanding gas shell collides with nearby molecular clouds, it triggers shock waves that can compress and destabilize the gas, potentially initiating new episodes of star formation. In this way, planetary nebulae serve as catalysts for cosmic renewal, ensuring that the process of stellar birth continues long after their parent stars have faded. Moreover, the presence of planetary nebulae in ancient stellar populations provides insights into the life cycles of low to intermediate mass stars. By studying these nebulae in globular clusters and distant galaxies, astronomers can trace how the chemical composition of stellar populations has changed over billions of years. This research is crucial for understanding how galaxies like the Milky Way have evolved, from their early stages as simple gas clouds to their current complexity. At the heart of every planetary nebula lies a white dwarf, a remnant core that represents the final stage of stellar evolution for Sun-like stars. These dense, Earth-sized objects contain the remnants of a once massive star, slowly radiating away their residual heat over billions of years. The study of these white dwarfs, facilitated by planetary nebulae, has provided invaluable insights into the behavior of degenerate matter and the physics of stellar cooling. Recent research has also suggested that some planetary nebulae may form in systems with multiple stellar components. In cases where a white dwarf exists in a binary system, mass transfer from a companion star can lead to a dramatic increase in its brightness, potentially triggering a nova, a sudden and powerful outburst caused by runaway nuclear reactions. These events add yet another layer of complexity to the role of planetary nebulae in shaping stellar evolution. The next generation of observational technology promises to revolutionize our understanding of the spectral observer. The Extremely Large Telescope, ELT, currently under construction, will offer unprecedented spatial resolution, allowing astronomers to resolve fine structures within nebulae with remarkable clarity. Additionally, new instruments such as the Nancy Grace Roman Space Telescope will provide wide-field surveys of planetary nebulae across diverse galactic environments, helping to refine models of their formation and evolution. Beyond optical astronomy, radio and X-ray telescopes will continue to probe the unseen aspects of planetary nebulae. X-ray observations, in particular, have revealed that some planetary nebulae contain hot, high-energy plasma, remnants of shock interactions between the expelled gas and the surrounding medium. These high-energy processes may play a significant role in dispersing nebular material over time, influencing the long-term fate of these structures. While planetary nebulae are primarily studied within the framework of astrophysics, they also occupy a special place in the human imagination. Their resemblance to eyes, celestial gateways, and ethereal forms has led many to interpret them as cosmic symbols of awareness and transformation. Across cultures, the eye has long been associated with knowledge, perception, and divine observation, and its counterpart in the stars, the Helix Nebula, often referred to as the Eye of God, has reinforced these associations. From a philosophical perspective, the heavenly sentinel serves as a reminder of the transient yet interconnected nature of all things. Stars are born, shine for millions or billions of years, and ultimately return their material to the cosmos, where it is reshaped into new stars, planets, and even living organisms. This cycle, echoed in the formation and dispersal of planetary nebulae, mirrors the broader principles of change, impermanence, and renewal that govern the universe. Ultimately, the study of planetary nebulae, the universal guardian of stellar evolution, offers profound insights not only into astrophysics but also into the broader mechanics of cosmic transformation. These nebulae are not merely the remnants of dying stars, they are active participants in the vast network of processes that shape the universe. From enriching the interstellar medium to triggering new waves of star formation, their impact is felt far beyond their luminous shells. As humanity's observational capabilities expand, so too does our understanding of the intricate dance between stellar life and death. The celestial guardian stands as a testament to the grandeur of cosmic evolution, a reminder that the universe is in constant motion, always shifting, reshaping, and preparing for what comes next. In the end, the story of the ethereal watcher is not just about stars, it is about us. The very atoms that make up our bodies were once forged in the hearts of ancient stars, released into space through the glowing remnants of planetary nebulae, and recycled into new worlds. In this way, we are all connected to the great cosmic cycle, living proof of the universe's ongoing symphony of creation and transformation. Thus, the spectral observer remains not only a scientific marvel but also a symbol of the endless possibilities that lie within the stars. It is a reminder that in every ending, there is a new beginning, an eternal cycle where the past shapes the future, and the light of dying stars illuminates the path toward new horizons. The astral gatekeeper, embodied in the ethereal glow of planetary nebulae, stands as a dynamic marker of the transition between stellar life and the vast interstellar medium. As these nebulae expand and disperse, they contribute not only to the ongoing chemical evolution of galaxies but also to the very fabric of cosmic transformation. Each one represents a singular moment in the grand cycle of star formation and death, a fleeting yet powerful display of nature's intricate processes. One of the most astonishing aspects of the celestial watcher is the diversity of its structures. No two planetary nebulae are exactly alike, despite originating from stars with similar masses. While some form near-perfect rings, others exhibit chaotic filaments, bipolar lobes, or even spiral arms stretching outward from the central star. This variety has led astronomers to investigate the external forces responsible for shaping these enigmatic formations. Among the leading explanations are magnetic fields, stellar winds, and the gravitational influence of unseen companion stars, each playing a role in determining a nebula's final appearance. As the expanding gas of the spectral guardian moves outward, its interactions with surrounding interstellar material create a series of shock fronts. These high-energy collisions result in the heating of the nebular gas, producing emission lines that reveal detailed information about its composition and motion. Spectroscopic studies using high-resolution telescopes have shown that different elements within a planetary nebula expand at different speeds, leading to layered structures where ionized hydrogen, oxygen, and nitrogen each form distinct glowing shells. The velocity of this expansion provides a crucial tool for determining the age of planetary nebulae. By measuring the outward motion of gas and extrapolating backward, astronomers can estimate when the ejection process began. Most planetary nebulae persist for only a few tens of thousands of years before they fade into the interstellar medium, making them relatively short-lived in astronomical terms. However, during this brief period, they serve as cosmic beacons, illuminating the processes that govern the final stages of stellar evolution. The galactic observer is more than a passive remnant of a dying star, it actively influences the environment around it. When the ejected gas collides with existing interstellar material, it can trigger star formation in nearby regions. This phenomenon, known as shock-induced star formation, occurs when compression waves create dense pockets of gas, providing the necessary conditions for gravitational collapse. In this way, the death of one star may directly lead to the birth of another, reinforcing the cyclical nature of cosmic evolution. Additionally, planetary nebulae provide an essential testing ground for understanding the life cycles of elements. The heavy elements expelled by these nebulae, carbon, oxygen, and nitrogen, become incorporated into future planetary systems, contributing to the formation of atmospheres and organic chemistry. Without the repeated enrichment provided by planetary nebulae, galaxies would remain chemically primitive, lacking the diversity of elements required for the complex chemistry seen in planets like Earth. One of the most compelling discoveries in recent planetary nebula research is the prevalence of binary systems among their progenitors. While single stars can produce relatively simple nebular shapes, binary companions introduce gravitational complexities that create strikingly intricate formations. In some cases, the companion star may even merge with the primary star, producing an especially dramatic ejection event. Observations of nebulae such as the Ant Nebula and the Hourglass Nebula have revealed spiral structures and bipolar outflows that suggest the presence of close-orbiting secondary stars. These formations provide valuable insight into the physics of binary evolution, offering clues about how stars exchange mass and energy in their final stages. Moreover, such interactions may play a role in the formation of more exotic astrophysical objects, including type Ia supernovae, which occur when a white dwarf accumulates enough material from a companion to trigger a runaway nuclear reaction. As astronomical instruments become increasingly sophisticated, the study of planetary nebulae is entering a new era. The James Webb Space Telescope, JWST, has already begun to unveil previously unseen details within these structures, offering unprecedented insights into their dust composition, gas dynamics, and internal energy sources. Future missions, such as the proposed LUVOIR, Large Ultraviolet Optical Infrared Surveyor, promise to extend these observations even further, allowing astronomers to detect planetary nebulae in distant galaxies and study their role in galactic evolution. One of the key areas of ongoing research involves determining how planetary nebulae evolve over time. By observing multiple nebulae at different stages of expansion, astronomers can construct models that predict how they change, from the initial ejection of gas to their eventual dispersal into the interstellar medium. These models are crucial for understanding not only the fate of individual stars but also the broader mechanisms that drive galaxy-wide chemical enrichment. Beyond their scientific significance, planetary nebulae have long captured the human imagination. Their resemblance to eyes, portals, or celestial symbols has led to a variety of interpretations, from religious and mythological connections to philosophical reflections on the nature of existence. The so-called Eye of God, as the Helix Nebula is often called, serves as a reminder of humanity's enduring fascination with the cosmos, a visual representation of the universe's watchful gaze, as if observing its own creation and transformation. Many cultures throughout history have associated the eye with knowledge, perception, and enlightenment, and its celestial counterpart in planetary nebulae reinforces this symbolic meaning. The study of these nebulae not only advances our scientific understanding but also connects us to a deeper appreciation of the universe's complexity and interconnectedness. The celestial sentinel embodies one of the most profound truths in astrophysics, that creation and destruction are not opposing forces, but two sides of the same cosmic process. The death of a star is not an end but a transformation, a release of material that will go on to form new worlds, new stars, and perhaps even new forms of life. As our knowledge of planetary nebulae grows, so too does our awareness of our own place in this vast, interconnected system. The atoms that make up our bodies were once forged in the fiery cores of ancient stars, released into space through planetary nebulae, and recycled into the Earth and everything on it. In this way, we are direct descendants of the stars, a testament to the ongoing cycle of cosmic rebirth. With each new discovery, the spectral guardian continues to unveil its secrets, guiding us toward a greater understanding of the universe. As technology advances, we will peer deeper into these celestial formations, uncovering new layers of complexity and refining our models of stellar evolution. Yet, no matter how much we learn, planetary nebulae will always remain a source of wonder and inspiration, a reminder that the universe is alive with motion, change, and infinite possibilities. Thus, the ethereal gatekeeper is more than just a fleeting stellar remnant, it is a symbol of continuity, a beacon of cosmic renewal, and a bridge between the past and the future. In its glowing filaments and radiant shells, we see the echoes of dying stars and the promise of worlds yet to be born, an eternal testament to the ceaseless transformation of the cosmos. The celestial sentinel, a luminous remnant of a once mighty star, remains a crucial player in the grand narrative of the universe's continuous transformation. Each planetary nebula represents both an ending and a beginning, an ephemeral moment when a dying star sheds its outer layers, only for that material to merge back into the vast interstellar medium, eventually seeding the birth of new stars and planetary systems. As these nebulae drift across the cosmos, they shape the evolution of galaxies, enrich the fabric of space with essential elements, and provide key insights into the physics of stellar life cycles. One of the most remarkable properties of the cosmic guardian is the way it interacts with radiation. The central white dwarf, a remnant of the original star's core, continues to emit intense ultraviolet light, ionizing the surrounding gas and causing it to glow. This process is responsible for the striking colors observed in planetary nebulae, with different elements emitting light at characteristic wavelengths. Oxygen typically glows green or blue, while nitrogen and hydrogen produce red and pink hues, forming the beautiful, otherworldly patterns seen in nebular images. The ionization process does more than illuminate the nebula, it actively shapes its evolution. As the gas absorbs radiation and heats up, it expands outward, creating pressure waves that interact with surrounding material. Over time, the nebula's structure changes, with dense knots of gas forming where matter clumps together, while other regions thin out as the gas disperses. These dynamic processes make each planetary nebula a living, evolving structure rather than a static remnant. New studies using infrared and radio telescopes have revealed the presence of dust grains within these nebulae, suggesting that planetary nebulae contribute significantly to the galactic dust cycle. This dust, composed of silicates, carbon compounds, and complex organic molecules, eventually integrates into star-forming regions, influencing the development of protoplanetary disks around young stars. This connection further underscores the role of planetary nebulae in the grand cycle of cosmic renewal. As the glowing clouds of a planetary nebula expand, they eventually fade into the background of the galaxy, leaving behind only a compact white dwarf. These stellar remnants, the end state of sun-like stars, are among the densest objects in the universe. Composed primarily of carbon and oxygen, they no longer generate energy through fusion but continue to radiate heat for billions of years. Over time, they cool and fade, becoming black dwarfs, though no black dwarf yet exists, as the universe is not old enough for any white dwarf to have fully cooled. Recent research into the cooling rates of white dwarfs associated with planetary nebulae has provided a new tool for measuring cosmic time. By studying the thermal evolution of these objects, astronomers can estimate the ages of stellar populations in different regions of the galaxy, refining our understanding of galactic formation and evolution. One of the most intriguing aspects of planetary nebulae is their potential connection to Type Ia supernovae. In binary systems where a white dwarf accumulates material from a companion star, it may eventually reach a critical mass, triggering a runaway nuclear reaction and resulting in a powerful explosion. These supernovae play a vital role in dispersing heavy elements across the cosmos and serve as standard candles for measuring astronomical distances. While not all white dwarfs in planetary nebulae reach this stage, their existence highlights the diverse evolutionary paths of stellar remnants and the profound role they play in shaping the chemical composition of the universe. Advancements in observational astronomy have revealed unexpected complexities in these nebulae, challenging earlier models of their formation. High-resolution imaging has uncovered intricate structures such as concentric shells, spirals, and dense knots of gas shaped by radiation pressure and stellar winds. Some nebulae, like the Cat's Eye and the Eskimo Nebula, feature layered envelopes, indicating multiple episodes of mass ejection separated by thousands of years. These findings suggest that the formation of a planetary nebula is not a singular event but a prolonged and dynamic process, where material is released in stages rather than expelled all at once. The diverse morphologies of planetary nebulae result from a combination of factors, including magnetic fields, binary star interactions, and variations in stellar wind intensity. These forces sculpt the nebulae into highly asymmetrical shapes, ranging from elliptical and bipolar structures to complex filaments and arcs. In some cases, interactions with interstellar clouds further distort their expansion, producing crescent-like formations. These interactions not only alter their appearance but also provide insights into the movement of stars within galaxies and the distribution of cosmic material. As astronomical technology advances, planetary nebulae are becoming more accessible to detailed study. The James Webb Space Telescope, JWST, has already begun revealing hidden molecular components within these nebulae, uncovering previously undetected compounds that may play a role in interstellar chemistry. At the same time, radio telescopes such as ALMA, Atacama Large Millimeter/Submillimeter Array, are mapping the distribution of cold gas and dust, offering a more complete understanding of their long-term evolution. These studies help astronomers piece together how planetary nebulae enrich the interstellar medium, seeding future generations of stars and planets. Future missions, including the Extremely Large Telescope, ELT, and the Nancy Grace Roman Space Telescope, will allow scientists to detect fainter nebulae in distant galaxies. By analyzing their composition and distribution, researchers will gain insights into how planetary nebulae contribute to the ongoing chemical evolution of different stellar populations across cosmic time. Additionally, advancements in computational modeling are enabling astronomers to simulate the formation and transformation of these nebulae with increasing accuracy. Incorporating elements such as fluid dynamics, radiation pressure, and magnetic interactions, these models bring us closer to understanding the full range of processes shaping these celestial structures. Beyond their scientific significance, planetary nebulae hold a deep symbolic and philosophical meaning. Their striking resemblance to eyes, portals, and celestial watchers has long captivated human imagination, inspiring artistic and spiritual interpretations. The Helix Nebula, often called the Eye of God, serves as a reminder of the vastness of the cosmos and humanity's enduring quest to understand its mysteries. These glowing remnants of once mighty stars invite contemplation, prompting us to reflect on the cycles of existence, the impermanence of all things, and the continuous transformation of matter and energy throughout the universe. At their core, planetary nebulae are more than just the remnants of dying stars. They are cosmic forges, dispersing elements that will one day coalesce into new stars, planets, and potentially even life itself. The oxygen in our atmosphere, the carbon in our bodies, and the nitrogen in our DNA were all forged in the fiery hearts of long-extinct stars, then cast into space through planetary nebulae before becoming part of new planetary systems. This grand cycle of stellar birth, death, and rebirth is not just an abstract astrophysical concept, it is the very process that made our own existence possible. Ultimately, planetary nebulae serve as bridges between stellar death and the creation of new celestial structures. Their ethereal beauty and scientific significance remind us that the universe is in a constant state of transformation. These nebulae are not merely fading echoes of dying stars but the seeds of future worlds. As they expand and disperse, they enrich the universe with the raw materials needed to form new stars, planetary atmospheres, and the chemical foundations of life. Through each new observation and discovery, we are not just studying the evolution of stars, we are witnessing the cosmic mechanisms that govern the universe itself. Planetary nebulae, fleeting in their lifespans yet essential in their contributions, remind us that nothing in the universe is truly lost. Every dying star contributes to the formation of new worlds, and every planetary nebula carries within it the legacy of past generations of celestial objects. The celestial guardian stands as both a scientific marvel and a profound cosmic symbol. It embodies the endless cycle of birth, destruction, and renewal that defines the universe. As we continue to explore these luminous remnants, we are not only uncovering the secrets of distant stars but also deepening our understanding of our own cosmic origins. In the vast and ever-changing cosmos, planetary nebulae remind us that the universe itself is a living, evolving entity, one where every ending is a new beginning, and every atom of our existence once belonged to a star that shone in the ancient night. Among the most striking celestial structures ever observed, this nebula stands out due to its nearly perfect geometric shape. Unlike most nebulae, which form through chaotic stellar outflows, its symmetry suggests that powerful, yet precisely controlled forces are shaping its structure. It is located thousands of light-years away, associated with a luminous central star undergoing significant mass loss. The surrounding material forms a complex web of dust and ionized gas, reflecting and scattering radiation in a way that enhances its unusual appearance. Observations in infrared and optical wavelengths reveal that the structure consists of highly organized lobes and equatorial rings. These features suggest the presence of either an intense magnetic field or a binary companion influencing the star's evolution. If a secondary star is present, its gravitational interaction could be sculpting the expanding gas, directing it along preferred axes. This would explain the sharp edges seen in the nebula and the apparent lack of chaotic turbulence that typically characterizes similar objects. The central star is likely in an advanced evolutionary stage, either approaching a transition to a Wolf-Rayet phase or nearing its final collapse. The material ejected into space could be part of a larger process in which layers of stellar atmosphere are shed over time, forming structured nebulae that persist long after the original outburst. The exact mechanism behind the symmetry remains a topic of ongoing study, with hypotheses ranging from episodic eruptions caused by internal instability to a controlled expansion influenced by a strong toroidal magnetic field. Spectroscopic analysis reveals that the nebula is rich in both silicate and carbon-based dust, suggesting complex chemical interactions occurring within its expanding shell. The presence of ionized hydrogen and oxygen lines indicates exposure to intense ultraviolet radiation, which is slowly altering the composition of the surrounding medium. These processes are crucial in enriching the interstellar environment with heavy elements that later contribute to the formation of new generations of stars and planetary systems. The velocity of the expanding gas suggests that the nebula has been evolving for thousands of years, though it is unclear whether it has remained stable over time or if it has undergone significant changes in structure. Some researchers propose that the formation is an optical illusion, where a more cylindrical or bipolar outflow appears squared due to our viewing angle. Others argue that external influences, such as a dense interstellar medium or remnant stellar winds, may be reinforcing the shape by constraining material along specific planes. Advanced telescopes equipped with high-resolution spectrographs are expected to provide more precise data on the velocity distribution of gas and dust. By analyzing how light interacts with different regions, astronomers hope to reconstruct the three-dimensional shape and determine whether the observed symmetry is an inherent property or a temporary phase. If the central star is approaching a supernova event, its surrounding nebula could dramatically brighten as the explosion interacts with the ejected material, similar to what has been observed in other massive star systems. Comparisons to other structured nebulae suggest that mass loss in massive stars follows patterns that are more organized than previously thought. While planetary nebulae often display symmetric forms due to the expansion of shells around dying stars, this particular object exhibits a level of precision that challenges conventional models. If magnetic forces are indeed playing a dominant role, it may suggest that similar structures could exist elsewhere but remain undetected due to their orientation or distance from Earth. Infrared observations have also hinted at the presence of complex organic molecules within the nebula, which could have formed through photochemical reactions triggered by high-energy radiation. Such environments are thought to be crucial in the early stages of planetary system development, as they contribute to the formation of prebiotic compounds that later become part of interstellar dust clouds. Understanding how these materials evolve in different stellar environments provides insight into the chemical diversity of the galaxy. Future research will focus on mapping the precise movement of gas within the nebula and determining whether external factors are influencing its evolution. If a binary companion is confirmed, it could provide further evidence that multiple star systems are a key factor in shaping structured nebulae. Long-term monitoring may reveal subtle shifts in brightness or morphology, indicating ongoing dynamic processes that have yet to be fully understood. If the central star eventually undergoes a supernova, it could transform the surrounding